Hello there, and welcome back to the Sleepless Scientist. Tonight we'll wander into space and time themselves. If you find comfort in these journeys, feel free to like and subscribe, only if it feels right. Leave a comment with where you are and what time it is. I love seeing how far these moments travel. Now dim the lights, let a soft hum fill the room, and let's begin. If your thoughts drift, that's fine. We'll still be here. Imagine, if you will, a universe in its twilight. Stars have burned out across the cosmic ocean. The galaxies are dim islands adrift in a sea that grows colder with every passing eon. Planets, once blue and green with life, have long since frozen into silent spheres. And yet, in a lonely corner of this future cosmos, a civilization lingers. They are unimaginably advanced by our standards, able to manipulate matter and energy with a mastery we can hardly picture. But even they face the same truth that all things must face. Time keeps moving, and the universe is running down. In their desperation to stretch out existence, they have turned to the strangest allies the cosmos ever offered: black holes. These dark giants, born from collapsed stars, warp the fabric of space and time itself. Near the event horizon, where gravity curves space-time into a funnel so steep that even light cannot escape, clocks tick differently. A moment for us might become an eternity for them, and so this civilization builds its refuge close to a black hole, hoping to slow the march of time. The idea is almost poetic. By clinging to the edge of a singularity, they are not simply surviving, they are negotiating with time itself, bargaining for more chapters in their story. To those far away, the civilization's last days might pass in the blink of an eye. To those living inside the distorted flow of hours near the black hole, centuries might unfold in what the rest of the cosmos would measure as mere moments. Time, in this strange corner, has become malleable, stretched like taffy, reshaped by the geometry of space-time. But despite this brilliant attempt, they cannot outrun the fate that physics has inscribed into the universe. The stars may flicker slower for them, the heat death may be delayed, but it is only a delay. Entropy, the slow drift from order to disorder, remains undefeated. Energy spreads thin, usable motion fades, and even the most elegant machines fall silent. Eventually, even black holes themselves evaporate through Hawking radiation, releasing their energy in the faintest whispers until nothing remains. This speculative frame is not meant to frighten you, but to invite you into a perspective shift. It shows us how space and time are not just backdrops, but participants in every story, even in the last story that might ever be told. It is also a reminder of how deeply mysterious these concepts are. What are we really speaking of when we say time is running out? What does it mean to say that space is expanding? Are time and space things containers, substances, or are they illusions emerging from something deeper and more hidden than we yet imagine? Throughout human history, thinkers have struggled with these questions. Philosophers sat beneath starlit skies and wondered whether time was something inside the mind or outside it. Physicists built equations to measure falling apples, orbiting planets, and bending light, only to discover that time and space slip away from our common sense when examined too closely. And in recent decades, some of the boldest voices have suggested that perhaps time and space do not exist at all, not as fundamental realities, but as emergent phenomena, rising out of patterns of information or webs of relation. The journey ahead will be long and winding, but always gentle. We will begin, in the ancient world, listening to voices like Plato, Aristotle and Augustine. We will follow the path to Newton, Leibniz and Galileo, who began to pin time to motion and space to geometry. We will travel into the age of relativity, when Einstein and Minkowski revealed that time is not universal, but flexible, relative, and intertwined with space. We will pause with thermodynamics, entropy, and the arrow of time, which tell us why we remember the past but not the future. and we'll step into the strange garden of quantum physics, where time sometimes disappears from the equations entirely, and where entanglement seems to weave the fabric of space itself. Along the way, we will return, again and again, to you, the human observer, the sleeper, the dreamer. For space and time are not only cosmic phenomena, they're also the quiet rhythms of your own life, the ticking of a bedside clock, the slow steeping of tea, the strange dilation of minutes when you wait in boredom, and the vanishing of hours when joy carries you forward. In this way, we're not only discussing the nature of the universe, but also the nature of your own experience of being alive. So let the image linger in your mind, a civilization at the edge of a black hole, holding out against the inevitable fade of the cosmos. Their fate may be sealed, but their defiance teaches us something. It teaches us that space and time are not neutral. They can be bent, stretched, manipulated, and perhaps even transcended. If such things are possible, then we must ask, what are space and time really? Are they the stage upon which existence plays out, or are they part of the performance, as ephemeral as the flicker of light across a stage curtain? As we set out, take a deep breath. Feel the quiet rhythm of your own heartbeat. Notice the subtle weight of each second as it passes. This is your black hole, your horizon, the now. And now, let us drift together into the oldest, deepest, and perhaps most soothing question of all. What is space and time? Picture yourself standing beneath a night sky before the age of telescopes, before the ticking of mechanical clocks, before mathematics had even given us the tools to describe motion in numbers. The world feels vast, but also immediate. The stars above look eternal, their patterns repeating each season, while the rhythm of sunrise and sunset keeps the cycle of daily life in motion. In such a setting, the first questions about time and space arose not from laboratories but from simple wonder, from ordinary human beings looking at the heavens and asking what it all meant. Plato, the philosopher of forms and ideal worlds, imagined space as a kind of receptacle, a container that could hold the shapes of all things. To him, it was less an object in itself and more a stage upon which the shadows of the eternal played out. Time, meanwhile, he described as the moving image of eternity, a reflection of perfection into the changing world we inhabit. There is something almost poetic in his view. The stars moving across the sky are not simply spheres of fire, but reminders of a deeper, timeless order. When you watch a clock hand sweep across its face today, you are echoing Plato's insight. That time as we live it is a shifting copy of something more enduring and strange. Aristotle, who came after Plato and often sought to ground ideas in more practical soil, disagreed with treating time as an independent entity. For him, time was not a thing but a measure. It was the number of change with respect to before and after. In other words, time exists only because things move, grow, and alter. If nothing ever changed, if no leaves ever fell and no hearts ever beat, there would be no time. Aristotle's view feels close to our ordinary intuition. You notice the passage of time when a candle burns down, when bread rises in the oven, when shadows shift across a wall. The change is the thing. Time is merely how you measure it. Centuries later, Augustine, the Christian philosopher and theologian, took the question of time inward. He confessed in his writings that he knew what time was until someone asked him to explain it. Then the knowledge slipped away. For Augustine, the problem was that the past is gone. The future is not yet, and only the present seems real. Yet even the present is fleeting, vanishing the instant we try to hold on to it. He suggested that time might live more in the mind than in the world. Memory stretches behind us, expectation reaches ahead, and attention anchors us in the now. If you have ever lost yourself in daydreams about tomorrow or nostalgia for yesterday, you have lived Augustine's puzzle. Is time something outside us or something inside? These ancient perspectives highlight a tension that has never left science or philosophy. Is time real in itself, flowing independently like a river? Or is it only a name we give to the order of events, a measure of change, a construction of perception? When you wait for a kettle to boil and it seems to take forever, you feel time as something dragging. When a joyful conversation erases an hour before you notice, you feel time as something light and slippery. Both are human experiences, but do they reflect the nature of time itself? Plato, Aristotle, and Augustine would each answer differently. Space, too, was mysterious. Without telescopes, ancient thinkers could only imagine what lay beyond the sky. Was space infinite, or bounded by a crystalline sphere? For Plato, space was an abstract backdrop. For Aristotle, the heavens were made of a fifth element, ether, moving in perfect circles unlike the imperfect decaying motions on Earth. To walk through a field or gaze across a valley was to sense space as distance. But for philosophers, it was also to wonder, does space exist on its own? Or is it simply the relations between things? If the stars vanished, would space remain? If you closed your eyes and imagined nothing at all, would there still be a place for something to be? We tend to think of these questions as abstract, but they're grounded in everyday life. Farmers needed to know when to plant seeds, sailors needed to track the stars for navigation, builders needed to measure lengths and angles. In the rhythm of seasons and the geometry of fields, space and time were already being measured long before they were theorized. A sundial carved from stone was both a tool and a philosophy lesson. It showed that shadows could reveal the invisible rhythm of the sun, that motion could be turned into numbers, and that time could be made visible. Yet for all these insights, contradictions remained. Plato elevated time to a reflection of eternity, while Aristotle tied it to motion. Augustine made it subjective, tied to human experience. These conflicting views are not errors, but steps on a path. They prepared the ground for later debates, where Newton and Leibniz would argue fiercely about whether time is absolute or relational. They also echo in modern physics, when we ask whether time is fundamental or emergent, whether space is a fabric or an illusion. When you look back on these early wonderings, it is striking how they still feel alive. To lie awake at night, staring at the ceiling, wondering why moments slip away, that is Augustine's question. To marvel at how seasons turn, crops grow, and rivers carve valleys, that is Aristotle's view of time as the measure of change. And to imagine that all this flux might be a reflection of a deeper, timeless reality, that is Plato whispering across millennia. The fact that these voices still speak to us suggests that the mystery of time and space is not simply scientific, but human. So as we leave the ancient world, we carry forward three threads: time as a reflection of eternity, time as the measure of change, and time as something shaped by perception. These threads will tangle and unravel as we move into later centuries, but they never vanish. They are woven into the way you feel the passing of hours to night as you listen, into the way scientists still debate the foundations of physics, and into the way poets describe the fleetingness of a single life. The story of time begins in philosophy, but it does not end there. It stretches forward, winding into experiments, equations, and discoveries yet to come. After the voices of Plato, Aristotle, and Augustine had set the stage, the world entered long centuries when questions of time and space were filtered through theology, faith, and the structures of medieval life. In monasteries, the ringing of bells regulated the day, marking hours of prayer and labour. For most people, time was not an abstract quantity measured on dials, but a rhythm carried by sunlight, harvest cycles, church rituals, and the human body itself. Space, meanwhile, was not thought of as infinite emptiness, but as a layered creation, with Earth at the centre, the heavens above, and the divine beyond. It was a world structured, ordered, and finite, where time was imagined as flowing from creation toward an ultimate end. In this medieval cosmos, Aristotelian ideas persisted. The heavens were seen as made of perfect spheres, moving eternally without decay. The earth, by contrast, was the realm of change, imperfection, and mortality. Time belonged to both realms, but it had a different quality depending on where one looked. Astronomers carefully charted the motions of planets, monks maintained records of eclipses and calendars, and scholars debated how time could be reconciled with divine eternity. For them, eternity was changeless, while time was the arena of change. The distinction echoed Plato's image of time as the moving shadow of eternity, yet it was also coloured by Augustine's confession that time might be more a matter of human perception than of cosmic machinery. Still, the centuries did not pass without questions. As medieval universities grew, translations of Greek and Arabic texts stirred debate. Thinkers such as Thomas Aquinas tried to weave Aristotle's philosophy into Christian theology, arguing that time and space were created by God, sustained by divine will, and not eternal in themselves. Others, working in the Islamic world, wrestled with similar issues, wondering whether time could be infinite into the past, or whether it had a beginning. These debates may seem distant, but they foreshadowed the way later scientists would wrestle with infinity, with the origin of the universe, and with the question of whether time itself has a first moment. Then came the Renaissance, with its spirit of questioning, its passion for measurement, and its confidence that the world could be understood by human reason. It was in this ferment that Galileo Galilei, the Italian mathematician and observer of the skies, took his place. Galileo did not simply accept ancient authority. He rolled balls down inclined planes, dropped objects from towers, and pointed a telescope at the heavens to see for himself. By doing so, he shifted the conversation about motion, space, and time from the realm of philosophy into the realm of experiment. One of Galileo's most important insights was the principle of relativity in motion. To him, there was no absolute state of rest. Imagine being in the cabin of a smoothly moving ship. If you dropped a ball, it would fall at your feet just as if the ship were at anchor. The motion of the ship, steady and uniform, could not be detected by any experiment inside the cabin. This idea may seem obvious now, but at the time it was radical. It suggested that motion is relative, that there is no universal backdrop of absolute stillness. The seed of relativity had been planted centuries before Einstein would bring it to full bloom. Galileo's experiments with falling bodies also changed how people thought about time. Aristotle had taught that heavier objects fall faster than lighter ones. Galileo, by careful observation, showed that all objects fall at the same rate, neglecting air resistance. To measure this, he used inclined planes to slow down motion so that he could count and compare. Here, time was no longer just the rhythm of bells or the cycle of the sun. It became a measurable quantity, something that could be marked, divided, and inserted into equations. Time was taking its first steps into mathematics. His telescope, meanwhile, revealed moons circling Jupiter, mountains on the moon, and countless stars invisible to the naked eye. The universe was larger and stranger than anyone had imagined. Space was not a neat set of spheres revolving around Earth. It was vast, dynamic, and filled with motion. Each new discovery cracked the old cosmic shell and suggested that both space and time were deeper mysteries than tradition had allowed. There is a quiet beauty in Galileo's courage. He did not set out to overthrow ancient wisdom, but by insisting on seeing for himself, he gave us a new relationship to reality. He showed that nature speaks in patterns, that those patterns can be measured, and that time itself could be turned into a line of numbers on a page. Imagine him in the stillness of night, ear pressed to the ticking of a water clock he used for timing experiments, watching a ball roll down a polished track and noting each moment with care. In those quiet hours, time ceased to be an abstraction. It became data, a tool for unlocking nature's secrets. And yet Galileo still carried the echoes of the ancients. He accepted that the heavens must be governed by order, even if he disagreed with Aristotle's account of how that order worked. He believed, like Plato, that mathematics reveal the deep structure of reality. His principle of relativity echoed Augustine's concern that time and space might not be as absolute as they appear. The old voices were not silenced. They were transformed into a dialogue that stretched across centuries. By the time Galileo was finished, the universe no longer seemed like a closed, finite chamber. It had begun to open, to stretch outward, and to reveal its secrets through the twin lenses of experiment and mathematics. Time was no longer just the rhythm of bells or the whispers of philosophers. It was a measurable, quantifiable element of the natural world, ready to be placed into equations. Space was no longer a fixed stage of crystal spheres. It was becoming a realm of infinite possibilities, waiting to be charted. As we prepare to step into the world of Newton and Leibniz, we can feel the shift. The Middle Ages had treated time and space as divine gifts, woven into creation. Galileo treated them as elements of nature to be measured and tested. From this shift, a new science would be born, a science that imagined the universe as a grand mechanical system running on invisible laws. The debate between absolute and relational time was about to be reignited, and this time it would shape the very foundations of physics. The 17th century was an age of clocks, both mechanical and philosophical. Town squares echoed with the striking of bells, merchants relied on portable watches, and astronomers synchronized their observations by counting pendulum swings. Time, which for centuries had been a mixture of ritual and rhythm, was suddenly becoming a matter of gears, weights, and precise mathematics. In this climate of invention and measurement, two towering figures, Isaac Newton and Gottfried Wilhelm Leibniz, shaped the debate about the nature of space and time in ways that continue to ripple through science today. Isaac Newton, with his flowing hair and relentless curiosity, imagined the universe as a grand stage. On this stage, planets revolved, apples fell, and cannonballs traced arcs through the sky. Space, in his view, was like an invisible container, infinite and unchanging. It existed whether or not anything occupied it. Time, likewise, flowed uniformly and inexorably, like a great river sweeping everything along at the same pace everywhere. It did not matter whether you were on Earth, Jupiter, or drifting between the stars. The ticks of time were the same. Newton called this absolute, true, and mathematical time. For him, it was the backdrop against which the drama of physics unfolded. This picture made extraordinary sense for the experiments and observations of his age. His laws of motion and universal gravitation worked beautifully when set upon this stage of absolute space and time. If you wanted to predict the orbit of the moon, or the swing of a pendulum, all you needed was to measure carefully, apply his equations, and trust that time was flowing evenly everywhere. Newton's vision was mechanical, but also elegant. The universe became a vast clock, wound at creation, ticking in steady rhythm forever. But not everyone agreed. Gottfried Wilhelm Leibniz, philosopher, mathematician and co-inventor of calculus, rejected the idea that space and time could exist independently of the objects and events they contained. For him, space was not a thing in itself, but a set of relations between objects. To say that two apples are a foot apart is meaningful. To say that space exists without any apples or stars or people is nonsense. Time, likewise, was not a flowing entity, but a way of describing the order of events. Without events there is no time. Without things there is no space. In his relational view, time is like the grammar of change, not the substance through which it flows. The debate between Newton and Leibniz was not just a quarrel of personalities, but a clash of metaphors. Newton's absolute time is like a metronome. ticking regardless of whether any musicians are playing. Leibniz's relational time is like the music itself, emerging only when notes are struck in sequence, which is closer to reality. The answer remained elusive. One of the famous thought experiments Newton used to defend his view involved a bucket of water. Imagine a bucket filled with water, suspended by a rope, twisted tightly, and then released. As the bucket spins, the surface of the water becomes concave, curving upward along the edges. Newton argued that this concavity showed that the water was rotating relative to absolute space itself, not just relative to the bucket. For Leibniz, however, such reasoning was unsatisfactory. He maintained that all motion, and thus all rotation, could only be understood in relation to other objects, not to some unseen, empty stage. The two men also disagreed on the role of God in this cosmic framework. Newton saw God as occasionally intervening to adjust the machinery of the universe, keeping it running smoothly. Leibniz countered that such tinkering would be unworthy of a perfect creator. A truly divine clockmaker would have designed a system needing no adjustments. Beneath their technical dispute lay profound questions about the nature of reality, divinity, and perfection. For centuries, Newton's vision dominated. His mechanics explained the motion of planets, the behaviour of tides, and even the paths of comets. Ships navigated oceans using his formulas, engineers built bridges in confidence, and scientists trusted that time and space were fixed, eternal and absolute. Yet the seeds of doubt remained. Leibniz's insistence that time is nothing without events would echo later in the work of Einstein and in the strange world of quantum mechanics, where time sometimes disappears from the equations altogether. There is something deeply human in this debate. Imagine sitting at a desk watching an hourglass. For Newton, the sand falls because time itself is flowing, carrying the grains downward as surely as a river carries leaves. For Leibniz, the falling sand is time. The order of grains passing from top to bottom is all there is. Which feels more natural? Perhaps both, depending on the mood. When you're waiting impatiently, time feels like an independent force dragging slowly forward. When you are absorbed in a task, time is invisible, inseparable from the events unfolding. Even today, ordinary language reflects Newton's legacy. We say we spend time, waste time, or save time, as though it were a resource flowing steadily through our lives. But our experiences often match Leibniz's view. A summer of new adventures stretches endlessly, while a year of repetitive routine shrinks in memory to almost nothing. These two perspectives, time as a universal current and time as the measure of change, are not mutually exclusive. They are two ways of sensing a mystery that has never been fully resolved. Newton's and Leibniz's legacies remind us that science is not only about equations, but about imagination. To picture the universe as a clock or as a grammar is to make a metaphor powerful enough to guide centuries of inquiry. Their clash of visions laid the groundwork for future revolutions. When Einstein arrived, he would both honour Newton's absolute time by showing how powerful it had been, and overturn it by proving that time could stretch, shrink, and warp. In Einstein's universe, Newton's river would become elastic, and Leibniz's insistence on relations would find new expression in the geometry of space-time. For now, though, in the 17th and 18th centuries, Newton reigned supreme. His clockwork cosmos gave confidence to explorers, engineers, and astronomers. The Industrial Revolution was timed by his invisible metronome, and the Age of Reason marched to its steady beat. Yet in the background, like a quiet counterpoint, Leibniz's voice whispered, "Perhaps time and space are not what they seem. Perhaps the stage is not real, only the play upon it." As we leave this chapter, we step from the tick of pendulums and the swirl of buckets into an era where new puzzles awaited. Light, electricity, and heat would challenge Newton's framework, hinting that absolute time might not survive unscathed. The river of time, once thought eternal, would soon begin to ripple. When philosophers and scientists speak of time, they often mean something grand and external, the ticking of the universe, the geometry of space-time, or the steady increase of entropy. Yet each of us carries another kind of time, quieter and more intimate. It is the time you feel when you wait for water to boil, when a joyful evening slips away unnoticed, or when a sleepless night stretches into an endless sequence of moments. This is subjective time, the inner rhythm that your brain creates as it registers change, attention, and memory. Understanding how we perceive time is not only fascinating in its own right, it also sheds light on why time feels so mysterious to us in the first place. Psychologists sometimes describe this perception as psychological time, a term that may sound like an invention of philosophy, but is rooted in experiments. People asked to estimate the duration of an interval rarely agree precisely, and their judgments vary with mood, focus, and even expectation. If you have ever stood in a long line at the post office staring at the clock, you know how minutes can expand into what feels like hours. Yet when you are absorbed in reading a novel or losing yourself in a conversation, hours can collapse into what feels like a moment. The difference lies not in the external march of seconds, which the clock keeps faithfully, but in how your mind allocates attention. When little is happening, your awareness magnifies each second. When your mind is occupied, you stop noticing the ticks of the clock altogether. This distortion becomes even more striking in moments of fear or danger. People who have been in car accidents often report that the events seem to unfold in slow motion. Neuroscientists suggest that under stress the brain creates denser memories, recording more details per second. When those memories are recalled later, the abundance of information gives the illusion that time itself slowed down. It is not that the world moved differently, but that the mind captured more frames of the film. What we call time is, in these moments, the depth of memory etched into the nervous system. Joy, by contrast, seems to erase the clock. When you are laughing with friends, walking under a sunset, or caught in the thrill of discovery, the brain pays less attention to time. It is in these moments that psychologists speak of flow, a state where you are fully immersed in the present task. In flow, minutes and hours blur, and when you finally resurface, you may be surprised at how much time has passed. Here, subjective time does not slow down as in fear, but simply recedes, leaving only the brightness of the experience. Culture adds its own layers. In English, we speak of time as a resource to be spent, saved, or wasted, reflecting Newton's idea of a uniform flow. But in other traditions, time is not a line or a river, but a landscape. In some Andean cultures, the past is described as in front, because it is visible and known, while the future is behind, because it cannot be seen. In some languages, the present is not a thin slice between past and future, but a broad field in which events unfold. These metaphors shape how we experience life. A person raised in one culture may rush to save time, while another may see no contradiction in waiting patiently, because time is not something that can be lost. Beneath these differences, biology provides the machinery. Deep in the brain lies the suprachiasmatic nucleus, a cluster of neurons that functions as our master clock. This cluster governs the circadian rhythm, the roughly 24-hour cycle of wakefulness, sleep, and body temperature. It keeps us aligned with the sun, adjusting when light enters the eyes. Without it, our daily rhythm would drift, as experiments with volunteers in windowless environments have shown. Yet this is not a stopwatch but a conductor, ensuring that hormones, alertness, and metabolism all follow a coordinated schedule. Your feeling of morning grogginess or late-night alertness is, in part, the song of this hidden clock. For shorter intervals, the brain seems to rely on pulses of neural activity, tiny bursts that are counted subconsciously. When you try to guess how long a minute has passed, you are unconsciously summing these pulses. Yet this system is far from perfect. Multitasking, distraction, or emotional upheaval can disrupt it, making seconds stretch or collapse. That is why time feels longest when you're waiting with nothing to do, and shortest when you're juggling many things at once. Memory also plays a central role. A childhood summer filled with novelty feels endless in recollection, because each day produced a rich store of impressions. By contrast, adult years, filled with routine, compress into a blur because there are fewer new markers to distinguish them. The paradox is that time may feel slow as it is lived but fast in memory, or fast as it is lived and slow in memory, depending on how much novelty and change the brain encounters. This duality makes the experience of time slippery, a fabric woven from both attention and recollection. Even the humble snooze button demonstrates how easily our internal sense of time falters. 9 minutes of half sleep between alarms seem shorter than any other 9 minutes of the day. Scientists have not pinned down why, but the best guess is that the disrupted state of semi-consciousness makes our inner clock unreliable. We drifted between wakefulness and dream, and the counting of seconds becomes hazy. It is as if the mind, not yet fully awake, gives up on measuring altogether. All of these examples show that time, as we live it, is not only physics but perception. You carry multiple clocks within you, circadian rhythms for days, pulse counts for seconds, memory for years. Each tells a slightly different story. Sometimes they align, and you feel time flowing smoothly. Sometimes they conflict, and you feel caught in distortions, long waits, sudden leaps, vanished hours. This is why the question, what is time, is so difficult. The brain itself creates different kinds of time depending on the scale, the context, and the emotional weight. When Augustine admitted that he could not define time, he was, in a sense, anticipating modern neuroscience. Time exists both outside us, in the motions of planets, and inside us, in the rhythms of neurons. To understand it fully, we must attend to both. In the next sessions, we will return to the external cosmic story, the arrows of entropy, the bending of space-time. But for now, it is worth pausing to recognize the mystery within your own head. As you listen to these words, your brain is not simply recording them in sequence. It is constructing a stream, shaping past sentences into memory, holding the current one in attention, and anticipating the next. This very act of listening is an experiment in time perception, so perhaps time is not only out there in the stars or in the equations of physics. Perhaps it's also here, in the quiet architecture of your brain, in the way you measure change without realizing it, in the way your memories stretch or compress, and in the way your emotions tilt the flow of moments. And perhaps that is why time feels so slippery, why it escapes every definition. It is not a single thing but a meeting point, between the cosmos and consciousness, between the tick of the universe and the pulse of the mind. When you think about time in an everyday sense, it feels natural to believe that only the present exists. The past has already slipped away, and the future has not yet arrived. What is real is what you see, hear, and feel right now. The warmth of the lamp on your desk, the sound of your own breathing, the faint pull of your heartbeat. This intuition forms the basis of what philosophers call presentism. According to this view, reality is like a spotlight moving along a line. The illuminated point, the present, is real, while everything before and after is not. Presentism has a certain comfort. It matches how you live moment to moment. It fits with the sense that life is fleeting, that the present is precious because it alone is guaranteed. When you taste a piece of fruit or hear laughter, the experience feels anchored in a now that cannot be repeated. Presentism tells us the past is a memory, the future a dream, but the present is life itself. Yet other philosophers and physicists have argued for a different picture. one that feels less intuitive but more consistent with what science suggests. This view is eternalism, also called the block universe. In this picture, past, present and future all exist equally, like different pages of a book. Just because you are reading page 100 does not mean page 50 has vanished, or page 200 does not yet exist. They are all there in the binding. Your consciousness moves from one to the next, but the book as a whole is complete. Eternalism can feel strange, even unsettling. It implies that the future already exists, that events we have not yet experienced are as real as the ones we remember. It suggests that free will might be an illusion, that our choices are part of a tapestry already woven. And yet, this idea fits neatly with Einstein's theory of relativity, which shows that there is no universal now. Two observers moving differently through space-time may disagree on whether events are simultaneous. Without a single cosmic present, the universe looks less like a moving spotlight, and more like a four-dimensional block, with all events laid out. Between these two positions lies a compromise known as the growing block theory. In this model, the past and present are real, but the future is not. The universe is like a block of marble that grows larger with each passing moment. Events are added as they happen, becoming fixed in the record of reality, while the future remains open. This view preserves some of the intuitions of presentism, the openness of the future, while also acknowledging that the past is not nothing but remains part of the structure of the universe. These three perspectives, presentism, eternalism, and the growing block, are not just abstract theories, they colour how we experience our lives. A presentist might focus on mindfulness, savouring each moment as uniquely real. An eternalist might find comfort in the thought that nothing is ever truly lost, that every smile and sorrow exists forever in the block of space-time. A growing block advocate might see life as a construction, building stone by stone, each day adding to the architecture of existence. Each view also reflects in the language we use. When you say, "the past is gone," you echo presentism. When you recall a memory so vividly that it feels as though you could step back into it, you hint at eternalism. When you speak of moving forward or building a future, you align with the growing block. Philosophy and ordinary speech are closer than we think. Modern physics complicates the picture further. Relativity's denial of an absolute present supports eternalism, but quantum mechanics, with its probabilistic unfolding, seems to preserve a sense of openness. The collapse of a wave function looks like the creation of a new present, a fresh addition to the block. The arrow of time, driven by entropy, adds another layer. We do not see time in reverse because entropy increases, making the future different from the past. Yet the laws of physics themselves are mostly time-symmetric. In their equations, nothing forbids events from running backward. It is only the low entropy of the early universe that gives us the familiar direction of past to future. There is also a psychological element. For you, the present feels special because it is the only point at which you are conscious. Your memories tie you to the past, your anticipations stretch into the future, but awareness itself is always bound to now. This moving present is an artifact of consciousness. Eternalism suggests that your future self is already out there in space-time, waiting, but your awareness has not yet reached that page of the book. Growing block theory says that future self is not yet written, only sketched as a possibility. Presentism says it does not exist at all until the moment arrives. Each interpretation is a way of explaining why the present feels so uniquely vivid. Consider everyday examples. When you look at photographs, you see eternalism, a past moment captured, preserved, still somehow real. When you watch a construction site, where foundations are laid and walls rise day by day, you see the growing block, the structure accumulating with each addition. And when you sit quietly, noticing your breath, the rustle of fabric, the warmth of a cup in your hand, you see presentism. The insistence that only this is real, that life is nothing but the unfolding now. None of these views can be easily dismissed. Presentism resonates with human intuition. Eternalism aligns with relativity and the geometry of space-time. The growing block strikes a balance that appeals to common sense. Perhaps the reason we cannot settle the question is that time is not a single thing, but a layered experience, appearing differently in physics, in consciousness, and in memory. Perhaps each model captures one aspect of a mystery too large to be contained in any single frame. As we leave this philosophical interlude, we carry a sense of how diverse our conceptions of time can be. Time can be fleeting, eternal, or ever-growing, depending on the lens. These debates are not just abstract. They shape how we think about life, mortality, and meaning. And as science advances, they remain relevant. In the centuries ahead, when physics speaks of space-time curvature or quantum entanglement, it is still shadowed by Augustine's question and Plato's reflections. The ancient voices and the philosophical models remind us that the mystery of time is not just mathematical, but existential. The next stage of our journey will return us to physics, where entropy and thermodynamics offer a new kind of arrow, pointing not to eternity or fleeting moments, but to disorder, memory, and the ultimate fate of the cosmos. When you look at the universe, it is easy to imagine that time flows simply because clocks tick, or because the Earth spins, but these are only markers, not causes. The deeper reason why time feels like an arrow, always pointing forward and never backward, is found in a principle that hides in plain sight. It is the second law of thermodynamics, a law that governs how energy is spread and how order gives way to disorder. This law can be stated in many ways, but its essence is simple. In any closed system, entropy tends to increase. Entropy is often described as disorder, but it is better understood as the number of ways a system can be arranged. A neat room can only be arranged in a few ways, but a messy room has countless possibilities. And so, left alone, things drift toward messiness, not because there is a will to disorder, but because disorder is statistically far more likely. This insight came from the work of Ludwig Boltzmann in the 19th century. He showed that entropy could be explained by statistics. If you imagine the positions and motions of all the particles in a gas, the overwhelming majority of arrangements look random. Only a tiny fraction produce neat patterns like all molecules clustered in one corner. And so, while it is not impossible for a scattered gas to spontaneously gather itself into order, the odds are so vanishingly small that it will never happen in practice. This explains why perfume disperses through a room but never gathers back into the bottle, why heat flows from hot coffee into the air but not back again, why eggs break but never reassemble. Each case is an expression of entropy's preference for the many over the few. From this statistical tendency comes the arrow of time. The laws of physics at a microscopic level, Newton's equations, or even the Schrödinger equation of quantum mechanics, are mostly reversible. They do not forbid particles from retracing their steps, but in practice, the second law ensures that macroscopic processes always move toward higher entropy. Once cream has swirled into coffee, you cannot unmix it. Once smoke has spread into the sky, you cannot collect it back into a neat plume. These familiar facts are not coincidences. They are the pulse of time itself. Think of your own life as a set of examples. When you clean your house, you expend energy, temporarily decreasing entropy in one corner of the world. But the energy you use, the calories you burn, the heat you release, all increase entropy elsewhere. The net balance is always upward. When you tidy your desk, the universe grows messier. The arrow of time is written in the dust you wipe away, in the dishes you wash, in the laundry that will inevitably be wrinkled again. The second law also connects deeply to memory. You remember the past but not the future because entropy increases. The present carries traces of lower entropy states. Footprints in sand, fossils in rock, digital photographs on a hard drive. These records are possible because the universe started in a state of low entropy and has been climbing upward ever since. If entropy were constant or already maximal, no such records could form, and the distinction between past and future would blur. In this way, the arrow of time and the arrow of memory are the same. This raises a profound question. Why did the universe begin in such a low entropy state? The Big Bang was not only hot and dense, it was also remarkably ordered. That improbability is what allows the arrow of time to exist at all. Without it, the universe might be timeless in practice, with no distinction between earlier and later. The fact that you feel time flowing, that you age, that stars burn and die, all rests on this extraordinary initial condition. Entropy also ties the everyday to the cosmic. The same principle that makes ice melt and wood burn also drives stars to shine and galaxies to evolve. A star is a delicate balance between the pull of gravity and the push of nuclear fusion, but over billions of years it runs down, releasing energy into space, raising entropy in the cosmos. A galaxy full of stars is like a vast engine, grinding toward higher disorder. On the largest scale, the universe itself may one day reach a state of heat death, in which all energy is evenly spread and no work can be done. Time in such a state would lose its meaning, for nothing new could ever happen. And yet entropy is not only decay, it is also creativity. The flow from order to disorder creates gradients, and gradients drive processes. Life exists because the sun is hot and space is cold, creating a flow of energy that can be harnessed by plants, animals, and ecosystems. Your body is a machine that uses these gradients to build complexity. Entropy increases overall, but in pockets, temporary islands of order form, cells, brains, societies. These islands are not violations of the second law, they are its consequences. Without entropy, nothing would change, and nothing could live. Boltzmann, who gave us the statistical understanding of entropy, saw the profound link between disorder and time. On his tombstone in Vienna, his formula for entropy is engraved, S equals K log W. It is a stark reminder that the arrow of time, which seems so mysterious when we feel it in our lives, is etched in the mathematics of probability. The simple truth that there are more messy states than neat ones explains why you age, why stars burn, and why the universe unfolds as it does. Of course, entropy has paradoxes. Loschmidt, a critic of Boltzmann, asked, "If the laws of physics are reversible, why does entropy increase at all? Could we not simply imagine every particle moving in reverse, undoing the arrow?" Boltzmann's answer was that such reversals are possible in theory but astronomically unlikely in practice. The probability of your shattered glass reassembling itself, or of smoke re-entering a chimney, is not zero, but so small it may as well be. Entropy rules not by law, but by overwhelming odds. So when you look at the world and see it moving forward, when you sense that tomorrow is not the same as yesterday, what you are truly witnessing is entropy's ascent. It is not a cruel law, but a gentle truth. Things fall apart more easily than they come together. And in that falling apart, in that drift or disorder, life and memory and history find their shape. Time's arrow is not painted across the sky. It is hidden in the quiet spread of molecules, in the dispersal of heat, in the statistical dance of countless particles. As we continue, we will look more closely at some puzzles entropy raises, such as Maxwell's demon, which seem to offer a loophole, and the deep connection between entropy and information, which tells us that time is not just about heat and disorder, but also about knowledge and memory. But for now, let the lesson settle. Time moves forward not because clocks tick, but because entropy grows. The second law of thermodynamics tells us that entropy tends to increase, that heat will not spontaneously flow from a cold body to a hot one, and that disorder is overwhelmingly more likely than order. It is such a sturdy principle that it has been called the only true law of physics that admits no exceptions. And yet, in the late 19th century, James Clerk Maxwell, best known for uniting electricity, magnetism and light into a single theory, posed a thought experiment that seemed to poke a hole in this iron rule. His challenge was not meant to overthrow the second law, but to test its foundations, to explore whether our understanding of entropy might be incomplete. The idea became famous as Maxwell's demon. Imagine a tiny being, invisible and quick, stationed at a door between two chambers of gas. The gas molecules, jostling and bouncing, are normally distributed with random speeds, some faster, some slower. The demon, with perfect vision, watches them carefully. Whenever a fast molecule approaches from the left, the demon opens the door and lets it pass to the right. Whenever a slow molecule comes from the right, the demon lets it slip to the left. Over time, the right chamber fills with fast, hot molecules while the left grows colder. In effect, the demon has created a temperature difference without expending energy, apparently reducing entropy in defiance of the second law. If such a creature existed, one might imagine it building perpetual motion machines, cooling rooms for free, and undoing the arrow of time itself. For decades, the demon haunted physics like a ghost at the feast. Scientists tried to identify where the trick lay. Some argued that the act of measurement itself must consume energy, or that the door required work to open. Others maintained that the second law was statistical and could allow local fluctuations, though Maxwell's demon seemed to produce them systematically. The puzzle lingered well into the 20th century until information theory offered a new perspective. In the 1960s, Rolf Landauer, working at IBM, proposed a subtle but profound insight. The demon's act of observing molecules is not the real issue. Observation alone can, in principle, be done without expending energy. The catch is memory. To decide which molecules to let through, the demon must record their speeds, store information, and then erase it to make room for new data. Landauer showed that erasing information is a physical act. It increases entropy by releasing heat into the environment. Thus, the demon cannot escape the second law, because the bookkeeping required to sort molecules inevitably produces disorder elsewhere. This realization reframed the problem. Entropy is not only about heat and disorder, it is also about information. To decrease entropy locally, you must pay the price of lost information, and that loss generates entropy in turn. Knowledge and thermodynamics are bound together. In other words, time's arrow is tied not just to energy dispersal, but also to the way information is handled. Think about memory in everyday life. When you delete a file from your computer, it is not an abstract act, but one that involves the rearrangement of physical states on a drive, the dissipation of energy, the release of heat. When you forget something, it is not that the brain simply leaves the information untouched. Neural pathways change, connections weaken, molecules rearrange. Forgetting in its own way adds to entropy. Even the act of tidying up your room requires you to remember where things go, and if you forget, disorder returns. Maxwell's demon, in this sense, was less a mischievous sprite and more a lesson in humility. Knowledge itself has thermodynamic weight. This connection has blossomed into what some call the information age of physics. Researchers now speak of entropy not only as the number of microscopic states, but also as a measure of information. Claude Shannon, the father of information theory, defined information entropy as the amount of uncertainty in a message. The two uses of the word entropy are not coincidental. Both describe how much is hidden, how much possibility exists. A disordered system is one with many possible states. A message filled with uncertainty is one with many possible interpretations. Physics and communication share a common language because both deal with the management of possibility. Seen this way, time's arrow is also the arrow of forgetting. The past is filled with records, photographs, fossils, memories, each a residue of lower entropy. The future, by contrast, contains no records. It has not yet left traces. As entropy grows, information about the past is preserved in marks and scars, while information about the future cannot yet exist. The direction of time is the direction in which information accumulates in one sense and erodes in another. Maxwell's demon also whispers into the field of computation. Every time a computer processes data, it manipulates bits, ones and zeros that are ultimately physical states of transistors, magnetic domains or photons. The second law ensures that computation cannot be perfectly free. Each logical operation is grounded in physical processes that generate heat. The limits of computation are, therefore, tied to entropy. Your laptop warming under your hands is a reminder that information processing is subject to the same arrow of time as stars burning or gases expanding. The demon also connects to questions of life. Living systems seem to resist entropy by creating order. Cells organize themselves, bodies maintain structure, ecosystems flourish. But life does not violate the second law, it dances with it. Organisms import low entropy energy, such as sunlight or food, and export higher entropy waste. Plants take photons from the sun, animals consume plants, and in the process, energy spreads, entropy rises. Life is Maxwell's demon on a grand scale, sorting and organising, but always paying the price in the larger universe. And so the paradox that once seemed like a threat to the second law has become a source of deeper understanding. Maxwell's demon teaches us that time's arrow is inseparable from the arrow of information. To know is to record is to store, and to store is to one day erase. Each of these acts is physical. They change the arrangement of matter and energy, and in doing so they reinforce entropy's rise. When you close your eyes and try to remember a childhood day, you're engaging in this dance of information and entropy. The memory is imperfect, blurred, shaped by time, because information degrades. The future is unknowable not because it does not exist in some cosmic sense, but because the information required to predict it is hidden, scattered, or destroyed by entropy. The demon at the door, opening and closing its gate, is a metaphor for every attempt we make to hold on to order against the tide. In the next step of our journey, we will see how this tide continues beyond thought experiments, shaping not only everyday life, but the fate of the cosmos. Entropy's ascent leads inexorably toward the heat death, the thinning out of usable energy, and the quieting of all processes. The demon cannot save us from this end, but in understanding its limits, we understand something profound. Time's arrow is written not just in matter and motion, but in knowledge, memory, and the very act of thinking. Entropy is not content to remain in the confines of teacups, kitchens, or computers. It stretches its reach across stars and galaxies, across billions of years, guiding the evolution of the universe itself. When you gaze up at the night sky, you're not only looking at scattered points of light, you're seeing engines of entropy at work, stars burning their fuel and spilling energy into the cosmos. From the first flicker of the Big Bang to the faint whispers of starlight we see today, the arrow of time has been propelled forward by this relentless drive toward disorder. And when cosmologists speak of the universe's distant future, they almost always invoke entropy, for it is entropy that writes the final chapter, the heat death. The idea of heat death emerged in the 19th century, when scientists first realized that energy, while conserved, could be transformed from useful to useless forms. A lump of coal can heat water and drive a steam engine, but once the heat has dispersed into the environment, it can no longer be gathered into concentrated work. The second law tells us that the universe too is subject to this drift. Over eons, stars burn out, galaxies grow dim, black holes evaporate, and the overall temperature of the cosmos slides toward uniformity. In such a state, everything is the same everywhere. Maximum entropy, perfect equilibrium. Without gradients of energy, there can be no processes, no change, no life. The universe would not end with a bang, but with a whisper, a slow fading into stillness. What makes this vision chilling is not only its inevitability, but also its contrast with the universe we know. The cosmos today is filled with energy differences. The sun is hotter than the Earth, and that difference drives winds, weather, and the biosphere. Stars shine because fusion in their cores maintains a temperature gradient with space. Even black holes, those ultimate sinks of entropy, possess differences in energy that shape their surroundings. Life itself thrives on these gradients, feeding on contrasts between hot and cold, concentrated and diffuse. If those contrasts vanish, existence loses its stage. Consider your own body as an example. You remain alive because you take in low entropy food and expel high entropy waste. If you try to live in a perfectly uniform environment, every particle the same temperature, every molecule evenly spread, you could not survive. There would be nothing to consume, no fuel to burn, no way to maintain structure. The same logic applies to the cosmos. Once every star has cooled, every galaxy has darkened, and every particle of matter has decayed or been spread evenly, the universe will be featureless and inert. How far in the future is this? Cosmologists measure it in unimaginable spans. In about 10 trillion years, star formation will cease. By then, most stars will have burned their fuel, leaving white dwarfs, neutron stars, and black holes. In another 100 trillion years, even these remnants will fade as white dwarfs cool and grow dark. On scales of 10 to the 40 years, black holes themselves will evaporate through Hawking radiation, releasing their mass as faint trickles of energy, until nothing remains but a thin mist of particles. At that point, entropy will have reached its maximum. The universe will be flat, featureless, and silent. And yet, there is an odd poetry in this. Heat death is not destruction but dispersal. It is the universe fulfilling the law that has guided it from the start. If the arrow of time is tied to entropy, then heat death is simply the arrow reaching its target. You might imagine it as a candle burning to its end, not extinguished by force but spent by its own flame. In this final state, the distinctions that define our lives, past and future, hot and cold, near and far, would blur. The arrow of time would lose its direction because nothing would change. Without change, without gradients, there is no way to tell before from after. Time, in a practical sense, would come to a stop. This idea is haunting, but it is also strangely serene. If the cosmos ends in heat death, it ends not in violence, but in quiet equilibrium. Everything has spread out evenly. Every potential difference has been resolved. Some thinkers even describe this as a kind of cosmic peace, the universe finally at rest after an existence filled with turbulence. Whether we see it as tragic or tranquil depends on our perspective. There are, of course, alternative scenarios. Some cosmologists speculate about a big crunch, in which expansion reverses and the universe collapses back into a dense state. Others imagine a big rip, where expansion accelerates so violently that galaxies, stars, and even atoms are torn apart. But the prevailing view, given current evidence of dark energy and accelerated expansion, is that heat death is the likeliest fate. The cosmos appears destined to expand forever, growing colder, thinner, and more uniform as entropy climbs. This vision connects back to the speculative image with which we began, the advanced civilization clinging to a black hole trying to slow time. In a universe heading toward heat death, such civilizations could only delay the inevitable. Black holes themselves, once thought eternal, are subject to entropy. They represent the highest entropy objects we know, their event horizons encoding vast amounts of information, but even they cannot last. As Hawking showed, they radiate, lose mass, and eventually dissolve. The most powerful fortress against entropy is still defeated by it in the end. And yet, this inevitability is not cause for despair. Entropy's rise is also the source of motion, of change, of life itself. Without entropy, stars would not shine, rivers would not flow, and memories would not form. The arrow of time that carries us toward heat, death is the same arrow that allows us to exist at all. Every heartbeat, every breath, every thought you have is made possible by the gradients entropy creates and destroys. Heat-death is not only the end, but also the condition for the middle. The flourishing of complexity, the rise of consciousness, the story of life. So when you think of entropy, do not imagine only decay. Imagine also the warmth of sunlight, the dance of molecules in a breeze, the way your own body maintains order by feeding on energy differences. Entropy is not the enemy of life, but its stage. The tragedy, if there is one, is not that entropy increases, but that it eventually leaves no gradients behind, and that end, so far in the future that human imagination strains to picture it, is less a catastrophe than a horizon. It is the sunset of the cosmos, painted not in flames, but in the fading of contrasts. As we move forward in our exploration, we will leave the vast future behind and return to the revolutions of the early 20th century. There, relativity and the geometry of space-time would show us that time is not absolute, and that space and time are bound together in ways that challenge both Newton and Leibniz. The arrow of entropy explains why time flows, but relativity will show us how time bends. For centuries after Newton, the image of time as a steady river flowing equally for all was unchallenged. Philosophers might argue, poets might doubt, but for practical science the model worked with such precision that few saw reason to question it. Then, in the early years of the 20th century, a young patent clerk named Albert Einstein asked a question that seemed innocent enough. What happens if you try to chase a beam of light? The answer he found would shake not only physics, but our very intuition of reality. Light had always been puzzling. In the 19th century, experiments by James Clerk Maxwell had revealed that light was an electromagnetic wave, travelling through space at a fixed speed, about 300,000 kilometers per second. But according to Newtonian mechanics, speeds should add. If you run toward a moving train, you encounter it faster. If you run away, you encounter it slower. By analogy, if you race toward a beam of light, you should measure it moving faster than if you ran alongside it. Yet every experiment suggested the opposite. No matter how you moved, the speed of light remained constant. It did not bend to the rules of addition. It was as though light was immune to the relativity of motion. Einstein's great leap was to take this stubborn fact not as a problem to be explained away, but as a truth to be accepted. If the speed of light is always the same, then it is space and time themselves that must adjust. From this insight grew the theory of special relativity, published in 1905, which transformed the structure of physics. It told us that space and time are not fixed backdrops, but flexible quantities that depend on motion. The faster you move, the more your measurement of length and duration diverges from someone else's. Consider the twin paradox, one of the most famous illustrations. Imagine a pair of twins. One remains on Earth, while the other boards a spacecraft and travels near the speed of light before returning. According to relativity, the travelling twin will have aged less than the one who stayed behind. From the Earth's perspective, the traveller's clock ticked more slowly. From the traveller's perspective, it was the Earth's clocks that ran slow. The symmetry seems puzzling, but the act of turning around breaks it. When the two reunite, their watches and bodies reveal the truth. Motion at near-light speed truly alters the flow of time. This effect is not hypothetical. Physicists have flown atomic clocks on airplanes and satellites, comparing them with clocks on the ground. The results are clear. Moving clocks run slower. Even the global positioning system, which relies on satellites orbiting Earth, must correct for relativistic effects. Without such corrections, your phone's map would place you kilometers away from your actual location. Each time you check directions, you're relying on Einstein's insight. The strange relativity of time has become an everyday necessity. Length, too, is altered. To an observer moving at high speed, objects in the direction of motion appear contracted. A spacecraft travelling near light speed seems shortened from the viewpoint of an external observer, though to those on board it feels unchanged. Time and space trade properties, flexing to preserve the constancy of light. The equations that describe this interplay are not abstract curiosities, but precise rules confirmed by countless experiments with particles accelerated to near-light speeds. Perhaps the most profound aspect of special relativity is that it dethrones the idea of a universal present. If two observers are moving relative to each other, they may disagree on whether two events happened at the same time. For one, the lightning may strike both ends of a train simultaneously. For the other, moving with the train, one strike may come before the other. Both are correct in their frames of reference. There is no single global now, no master, clock ticking above the cosmos. Time is relative, bound to the state of motion of the observer. This challenges our deepest intuitions. We live as though there is a common present binding us all, as though the moment you're reading these words and the moment someone else is doing so elsewhere are part of the same now. Relativity tells us that this is an illusion. The concept of simultaneity is local, not universal. Each observer carries their own slice of time, shaped by motion. The block universe we glimpsed earlier begins to take form here. All events exist, but their order depends on the observer. Einstein's theory also revealed the famous relation between mass and energy, expressed in the deceptively simple equation E=mc². This identity tells us that mass is a form of energy, bound in the structure of matter. Though not directly about time, this relation hints at the interconnectedness of concepts once thought separate. Energy, motion, space, and time are woven into a single fabric. In daily life, we do not notice these effects. At the speeds we move, cars, planes, even rockets, the distortions of time and space are minuscule. A flight across the Atlantic produces a time difference of only nanoseconds. But on cosmic scales, or in the laboratory where particles approach the speed of light, relativity is indispensable. Without it, our understanding of stars, galaxies, and the universe itself would collapse. Relativity also shifted our sense of humility. Newton's universe had seemed mechanical but secure. Time ticked uniformly, space stretched endlessly, and the laws were the same for all. Einstein showed that time is elastic, space is pliable, and what you observe depends on where and how you move. There is no privileged viewpoint, no cosmic observer holding the true clock. Each perspective is valid. Reality is more democratic than we once imagined. And yet, special relativity is only the beginning. It addresses observers moving at constant speeds, not accelerating ones, and it treats gravity as though it did not exist. But gravity could not be ignored for long. The bending of starlight, the fall of an apple, the orbit of planets, all demanded explanation within this new framework. Within a decade, Einstein would extend his insight into the general theory of relativity, where space and time themselves would curve, giving rise to black holes, gravitational waves, and a cosmos far stranger than Newton ever imagined. For now, special relativity leaves us with a lesson that continues to echo. Time is not absolute. It does not march in step for all. Instead, it dances with motion, stretching and shrinking to preserve the speed of light. The arrow of time remains, carried by entropy, but relativity shows that its pace is not uniform. To move quickly is to slow your passage through time. To stand still is to glide along more swiftly. And in this dance, light itself remains the metronome, unchanging, constant, the ultimate speed limit of the universe. Einstein's special relativity had barely begun to circulate when one of his old teachers, Hermann Minkowski, stepped forward with a startling declaration. In 1908, he announced that the revolution in physics was not merely about time moving differently for different observers. It was deeper. Space and time, once thought of as distinct arenas, were in fact inseparable. They formed a single four-dimensional continuum, spacetime. Einstein had changed the rules, but Minkowski redrew the stage itself. His words carried an almost poetic force. Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. To understand what Minkowski meant, it helps to picture events not as moments that occur in time alone, but as points in a larger landscape. Suppose you light a match in a dark room. The flame flares for an instant, sending photons racing outward in every direction. In ordinary thinking, we might say the flame occurred at a place and at a time. This corner of the room at 8 o'clock in the evening. But Minkowski tells us the event is better understood as a dot in space-time, a coordinate in both position and duration. The flare is not just here, then, but here and then, fixed in the four-dimensional fabric. From this perspective, every person, object and particle traces a line through space-time called a world line. Your world line begins with your birth, snakes through every place you have been, and continues until your final moment. Right now, as you sit and breathe, you are tracing your world line 1 second per second, moving relentlessly forward along the time axis. If you travel, your world line tilts through space, but it never leaves space-time, for there is nowhere else to go. In Minkowski's view, life is not a succession of fleeting moments, but a continuous thread woven into the tapestry of space-time. One of the most striking consequences of this picture is the structure of light cones. Imagine shining a flashlight at midnight. The beam spreads outward, carving a cone-shaped region into the future. Every possible event that could be influenced by your flashlight, every particle that could absorb one of its photons, lies inside that cone. Outside the cone, no signal can reach. Similarly, if you trace backward, every event that could have influenced the present lies inside a past-like cone. These cones define the limits of cause and effect. They show that the universe is not only structured by laws, but bounded by geometry. Nothing can outrun the spread of light, and so causality itself is built into the angles of space-time. Relativity of simultaneity also finds its natural explanation here. Two events may lie outside each other's light cones. For one observer, they appear simultaneous. For another, moving differently, one comes before the other. Both are correct, because the ordering depends on how your world line slices through space-time. This realization challenges our instinct to think of the present as universal. Minkowski's framework dissolves that comfort. The present is relative, not absolute. The block universe, hinted at in philosophy, takes on geometric clarity here. All events exist in the fabric, their order depending on your path through it. If this sounds abstract, consider a simple train analogy. A long train races across the countryside. A passenger in the middle sees lightning strike both ends at once, but an observer standing on the ground sees the strike at the front first, because the train is moving toward it, and the strike at the back later. In Newtonian physics, one of them must be wrong. In relativity, both are right, for simultaneity itself has no universal meaning. Minkowski's geometry explains why. Their world lines slice space-time differently, and so they divide the sequence of events differently. Reality is not broken, our intuitions are. This union of space and time also provides the framework for understanding energy and momentum. In Newton's world, momentum described motion in space, and energy described motion in time. In Minkowski's space-time, these combine into a single four-vector, obeying conservation laws that apply across the continuum. Physics, once a patchwork of separate quantities, becomes more elegant. It is as if mathematics itself were whispering. The universe is not two realms stitched together, but one fabric with four threads. Minkowski's idea also gave Einstein the tools to move further. When he later developed general relativity, the theory of curved spacetime, it was Minkowski's geometry that formed the scaffolding. Without the vision of a four-dimensional fabric, Einstein's equations might have been impossible to write. What began as a mathematical insight became the cornerstone of modern cosmology, but beyond the technical power, there is a philosophical resonance. To think of your life as a world line is to see yourself not as a collection of fleeting instants, but as a whole trajectory. Your past is not gone. It is part of the fabric. Your future is not unreal. It is simply not yet reached by your present awareness. Eternalism, the block universe view, finds its natural home in Minkowski's geometry. The book of space-time is already written, and we are readers moving through its pages one line at a time. Of course, whether this interpretation is literally true remains debated. Many physicists accept the geometry, but resist the philosophical leap. Yet the image remains compelling. When you walk through a quiet street, you're not only moving in space, but inscribing another section of your world line. When you pause to tie your shoes, you're not halting time, but tracing it differently. Each action, however small, becomes part of the grand design. So next time you look at the stars, consider them not as scattered points in the sky, but as glowing intersections of world lines, each shining from its own coordinate in space-time. Their light, reaching you after years or millennia of travel, carries the imprint of their past cones into your present. You, in turn, become part of their future cone. Minkowski's vision makes the universe feel less like a stage with actors, and more like a woven story where everything is connected, not just in space, not just in time, but in space-time. As we move on, we will see how this fabric bends under the weight of matter and energy. Einstein's general relativity will take Minkowski's flat geometry and curve it into valleys and hills, where clocks tick differently depending on where they rest, and where gravity is no longer a force but the shape of space-time itself. The marriage of space and time is only the beginning. Their flexibility, their malleability, will soon take us into the heart of stars and the darkness of black holes. If special relativity was a revelation, showing that time and space are flexible, tied to motion, and inseparable from the constancy of light, then general relativity was something even more audacious. It suggested that space and time are not only fused into a single continuum, but that this continuum itself can curve, stretch, and ripple. Einstein once said that in creating the theory he merely followed where mathematics and logic led, but it is hard not to see it as a leap of genius. The world had thought of gravity as a force pulling at a distance, a mysterious tug reaching invisibly across space. After general relativity, gravity became nothing more and nothing less than geometry. Einstein arrived at this insight through a moment he later described as the happiest thought of his life. He realized that a person in free fall does not feel their own weight. If you're in an elevator whose cables have snapped, you would float inside as though weightless, just like an astronaut in orbit. This equivalence between free fall and weightlessness suggested that gravity is not a force acting upon you, but a property of the frame you inhabit. Extend that idea, and you find that gravity is the curvature of space-time itself, shaping the paths along which objects move. To picture this, imagine stretching a rubber sheet and placing a heavy ball at its centre. The sheet dips, and smaller balls placed nearby roll inward, not because the heavy ball exerts a mysterious attraction, but because the sheet itself curves. General relativity tells us that the universe works the same way. Mass and energy tell space-time how to curve, and space-time tells matter how to move. The Earth orbits the Sun not because it is pulled by an invisible force, but because the Sun bends space-time around it, and the Earth follows the natural curve. One of the most immediate predictions of general relativity was that time itself is affected by gravity. In a strong gravitational field, clocks run more slowly. This is not a matter of mechanical interference, but a property of space-time itself. Time dilates near massive bodies. A clock placed on the surface of the Earth ticks more slowly than one placed on a mountain peak, where gravity's grip is slightly weaker. The difference is tiny, but measurable. Astronauts orbiting high above Earth experience time passing just a little faster than their counterparts on the ground. Over years, the divergence adds up to microseconds, small yet real. This gravitational time dilation is not just a curiosity, it has practical consequences in the modern world. The satellites that form the global positioning system orbit high above Earth, where gravity is weaker, and so their clocks run faster than ground-based ones. Engineers must correct for this, or else the navigation on your phone would drift by kilometres. Each time you check directions, you are unknowingly relying on Einstein's general relativity. The theory is not abstract, it is embedded in the way you find a cafe, catch a train, or locate a friend's address. General relativity also predicted that light itself would bend when passing near a massive body. During a solar eclipse in 1919, astronomers measured the apparent positions of stars near the Sun and found them shifted, exactly as Einstein's equations predicted. The announcement made Einstein a global celebrity. Suddenly the world knew his name, and physics had a new foundation. Space and time were not rigid containers but dynamic actors, flexing and responding to mass and energy. The theory further implied that massive bodies could create such deep wells of curvature that nothing, not even light, could escape. These are black holes, objects so extreme that they seemed at first like mathematical curiosities. Yet over the decades, evidence for them mounted. Today, we know that the centres of galaxies harbour supermassive black holes, millions of times the mass of the Sun, shaping the motions of stars around them. In 2019, astronomers captured the first direct image of a black hole's shadow in galaxy M87, a luminous ring surrounding darkness, the geometry of space-time itself made visible. General relativity also foretold gravitational waves, ripples in space-time launched by massive objects accelerating, such as pairs of black holes spiralling together. For a century, these waves remained elusive, but in 2015 detectors on Earth measured them directly for the first time. Two black holes collided more than 1 billion light-years away, and the faint stretching of space-time passed through Earth like a distant whisper. The detection was hailed as one of the greatest triumphs of physics, a direct confirmation that space-time is not a passive arena but a fabric that flexes and vibrates. There is something deeply humbling in all of this. General relativity turns gravity, once the most familiar of forces, into something alien and beautiful. You do not fall because the Earth pulls you, but because space-time is curved beneath your feet. You do not orbit because the Sun tugs at you, but because you are following a path laid down by geometry. Even your sense of time is altered by the depth of the gravitational well you inhabit. Time passes differently in valleys and on mountaintops, in orbit and on the ground. Time is not universal. It is sculpted by the shape of the cosmos. For everyday life, the differences are negligible. You do not feel your watch slowing at the bottom of a hill. You do not notice your heartbeat subtly altered by altitude. But for the universe at large, these effects dominate. Stars collapse into black holes. Galaxies dance under gravity's influence. Light bends across billions of light years to form the arcs and rings astronomers call gravitational lenses. The geometry of space-time is the architect of cosmic structure. And yet, even this magnificent theory has limits. General relativity works exquisitely well on large scales, describing planets, stars, and galaxies. But on the smallest scales, the quantum realm, it falters. The smooth fabric of space-time becomes incompatible with the grainy probabilities of quantum mechanics. Somewhere, hidden beyond our current understanding, lies a deeper theory that unites the two. But before we step into that struggle, it is worth pausing to admire general relativity for what it is, one of the most profound achievements of the human mind. A vision of the universe where geometry and time entwine to create the dance of reality. Einstein's equations of general relativity were more than just a new description of gravity. They were also a set of instructions for how the universe itself must behave. The mathematics did not only describe planets circling stars or light bending near the sun, they could be applied to the entire cosmos, and when they were, they revealed something astonishing. The universe could not remain static. It had to change, either expanding or contracting. This was unsettling to Einstein, who, like many of his contemporaries, preferred a timeless, eternal universe. He added a cosmological constant to his equations to counteract the natural expansion they predicted, a kind of mathematical bandage to preserve a steady cosmos. But the universe itself was under no obligation to honour his preferences. In the 1920s, astronomer Edwin Hubble, working with the great telescopes at Mount Wilson, began to measure the light from distant galaxies. By carefully examining the spectra of these galaxies, he found that their light was redshifted. The wavelengths stretched, as if the galaxies were moving away from us. The farther away a galaxy was, the more its light was shifted. Hubble announced that the universe was expanding, that space itself was stretching, carrying galaxies apart like raisins in rising dough. What had once been an abstract mathematical possibility in Einstein's equations became an observational fact. The cosmos was not static. It was dynamic, restless, alive with motion. The idea that the universe expands is easy to misunderstand. It is tempting to picture galaxies flying through space like shrapnel from an explosion. But the truth is subtler. The galaxy is not rushing outward into emptiness. Instead, it is space itself that expands. The distances between galaxies grow because the fabric of space-time stretches. To return to the raisin bread analogy, the raisins do not move of their own accord. As the dough rises, the distance between raisins increases. Each raisin sees the others moving away, and none can claim to be the true centre of expansion. The same is true of galaxies. Every galaxy observes the others retreating, and each could imagine itself at the middle. But in truth, there is no centre. The expansion is everywhere. This realization reshaped our sense of time as well as space. If the universe is expanding now, then in the past it must have been smaller, denser, hotter. Run the film backward, and you arrive at a moment when everything was compressed into a single, unimaginably dense point. This is the idea of the Big Bang. Not an explosion in space, but an expansion of space itself. Time and space, as far as we can tell, had their beginning in that moment. The flow of time is not eternal in both directions. It has a starting line. Einstein, who had once resisted the notion of expansion, later admitted his cosmological constant was his greatest blunder. Ironically, modern cosmology has found reason to revive it in a new form, but we will come to that later. For now, the important lesson is that general relativity transformed the universe from a fixed backdrop into a living, changing entity. Time is not just the measure of change within the universe. Time itself is part of the universe's change. Everyday analogies can help ground this cosmic picture. Imagine you are drawing dots on a balloon. As you inflate the balloon, the dots move farther apart. No dot is the centre of expansion. The surface itself stretches, carrying the dots along. That is how galaxies drift apart, not by flying through space, but by being carried by space's expansion. Or think of an old photograph album. As you flip through the pages, you see people grow older, fashions change, buildings rise and fall. In the same way, astronomers who look farther into space are looking back in time because light takes time to travel. A galaxy whose light has taken 10 billion years to reach us is not seen as it is now, but as it was when the universe was younger, smaller, and hotter. The telescope is a time machine, and the expanding universe makes its operation possible. The expansion also carries profound philosophical weight. It tells us that the universe has a history, that there was once a time when stars and galaxies did not exist, when matter was a hot plasma. when even atoms had not yet formed. It suggests that the arrow of time is inscribed not only in entropy, but in the very fabric of cosmic growth. The universe is not eternal. Repetition but unfolding narrative with a beginning, a middle, and, perhaps, an end. At first, the notion of expansion disturbed many. Some preferred the idea of a steady-state universe, where new matter was continuously created to fill the gaps as galaxies receded. This model preserved an eternal cosmos without a beginning. But as evidence accumulated, the discovery of the cosmic microwave background radiation, the faint afterglow of the Big Bang, the steady-state view gave way. The universe was indeed expanding, and it had indeed begun in a hot, dense state. For Einstein's equations, this was not a surprise. They had whispered it all along. The curvature of space-time is dynamic. It cannot remain frozen. If matter and energy fill the universe, then space-time must respond, bending and stretching accordingly. Expansion is not an accident, but a requirement of the geometry. The fabric itself breathes, and we are caught within its rhythm. Even now the expansion continues. Galaxies drift farther away each second, their light stretched redder and fainter. For us, in the short span of human life, the change is imperceptible. But on cosmic timescales, it is decisive. The night sky of the distant future will look emptier as galaxies recede beyond the horizon of visibility. The universe will grow lonelier, a consequence not of destruction, but of distance. In this vision, time itself seems to take on a double face. On one scale, we live in minutes and hours guided by clocks and calendars. On another, we live in epochs defined by expansion, where billions of years mark the unfolding of galaxies. The arrow of entropy and the arrow of expansion are distinct yet intertwined. Both move forward, and both shape our understanding of the cosmos. As we prepare to continue, we will turn to a puzzling feature of this expansion, its apparent violation of energy conservation. For in Newton's world, energy was sacred, neither created nor destroyed. But in a universe where space-time itself stretches, the concept becomes slippery. Photons lose energy as they redshift, and yet there is no reservoir from which that energy is drawn. The paradox of conservation in an expanding cosmos awaits us, a reminder that even our most trusted principles may bend when space and time themselves refuse to remain still. In the physics classroom, one of the first principles we learn is that energy is conserved. It can change form, potential into kinetic, heat into light, chemical into motion, but the total remains constant. The universe, we are told, plays fair with its books. Nothing is gained, nothing is lost. Yet in the context of an expanding universe, this principle becomes less clear, and the very idea of conservation begins to blur. Consider light from a distant galaxy. As space expands, the wavelength of that light stretches, shifting toward the red end of the spectrum. A photon that began its journey as high-energy blue light may arrive as lower-energy red light. In Newton's framework, such a loss of energy would demand an account. Where did it go? Who keeps the ledger balanced? In a universe governed by general relativity, the answer is subtler. The concept of global energy conservation does not hold in the same way, because space-time itself is dynamic, and its stretching does not conserve energy in the traditional sense. This can feel deeply unsettling. Energy conservation is so ingrained in our thinking that its violation seems almost sacrilegious. But general relativity operates with different rules. The law of energy conservation applies neatly in systems where space-time is static or nearly so, but in a universe where space-time itself grows, contracts, and curves, energy can change in ways that defy classical bookkeeping. The redshift of photons is not a transfer of energy from one place to another. It is a consequence of the stretching of the arena itself. In a sense, the energy simply fades, not into a reservoir but into the expansion. A useful analogy is sound in a balloon. If you trap a tone within a balloon and then inflate it, the sound waves stretch, their frequency dropping. The energy of the sound diminishes, not because it has been absorbed by anything, but because the space in which it travels has altered. The balloon does not keep a ledger of energy lost. The very idea of accounting does not apply in the same way. So too with the universe. As space expands, the photons dilute, their wavelengths stretch, and their energies decrease. There is no balance sheet that restores the loss. This leads to an important distinction. On local scales, where gravity binds systems tightly, within galaxies, solar systems, or even laboratory experiments, energy conservation still holds. If you toss a ball upward, its energy of motion is converted to gravitational potential, and then back again as it falls. If you run a generator, the mechanical work becomes electrical energy. The equations balance. But on the grand cosmic scale, where expansion dominates, the principle does not apply in the old way. The universe does not keep global conservation accounts. Instead, it follows Einstein's equations, which describe how space-time curves and evolves. Within that framework, energy as a global quantity is simply not well defined. Dark energy adds another layer to the puzzle. Discovered in the late 20th century, dark energy is the name we give to the mysterious driver of the universe's accelerated expansion. Unlike ordinary matter or radiation, whose energy density diminishes as the universe grows, dark energy's density seems to remain constant. This means that as space expands, more dark energy appears, filling the new volume. Where does this energy come from? Again, the question may be ill-posed. General relativity does not demand a source in the traditional sense. The equations allow the fabric itself to produce this effect without violating their structure. To our classical intuition, however, it seems as though energy is being created out of nothing. Everyday experience provides a contrast that helps highlight the strangeness. When you let a cup of tea cool, the energy lost from the tea is gained by the surrounding air. The total remains the same. But when photons lose energy to cosmic redshift, there is no corresponding gain elsewhere. The loss is absolute. Likewise, when dark energy causes the universe to expand faster, there is no external source adding to the tally. The system is self-contained, yet not bound by the conservation we expect. It is as though the cosmos has its own rules, different from the tidy ledgers of human engineering. This realization does not mean that physics has abandoned the concept of conservation altogether. In fact, conservation laws remain central, but they are expressed differently. General relativity ensures local conservation. In small regions where space-time can be treated as approximately flat, energy and momentum are conserved. It is only when we ask about the universe as a whole that the notion falters. There is no single global frame in which energy can be meaningfully measured across all of space-time. Without such a frame, the law cannot apply in the way we expect. Some philosophers of science find this liberating. It suggests that our intuitions, built from life in stable environments, may not be guides to cosmic truth. Others find it troubling, as though a cornerstone of reason has crumbled, yet the universe itself remains unmoved. Whether we like it or not, photons still redshift, galaxies still drift apart, and dark energy continues its work. The cosmos does not answer to our preferences for neatness. It may help to think of time itself as part of this strangeness. Conservation of energy assumes a background where time is uniform and absolute, a river against which flows can be measured. But relativity dissolves that background. Time is woven into space-time, which is dynamic. When the river itself bends and stretches, the old rules of conservation no longer hold. Asking where the lost energy of redshifted photons went is like asking where the minutes go when the clock strikes midnight. The question presumes a container that does not exist. This perspective can be disorienting, but it is also beautiful. It shows us that the universe is not a machine running on simple gears, but a living geometry, flexing and changing in ways that exceed our early intuitions. It tells us that even our most sacred principles must bow to the fabric of space-time, and it invites us to wonder whether energy, like time and space, might not be fundamental at all but emergent, a concept that works locally but dissolves when stretched across the cosmos. As we step forward, the paradox of energy in an expanding space-time becomes a bridge to deeper mysteries. It prepares us for the philosophical questions raised by relativity. If simultaneity is relative, and if energy conservation dissolves at cosmic scales, what does this mean for our sense of a universal present? Are past, present and future equally real in the block universe suggested by Minkowski and Einstein? Does the arrow of entropy flow through a timeless fabric, or is it itself a sign that time is real? These are the questions that await us in the next stage, where physics and philosophy meet at the boundaries of knowledge. To live as a human being is to be anchored in the present. The taste of a meal, the warmth of sunlight on your skin, the sound of a friend's voice. These things feel unquestionably real. The past exists only in memory, the future only in imagination, but the present feels solid, undeniable, the one place where existence truly happens. And yet, modern physics whispers a disquieting truth. The present, as we commonly understand it, may be an illusion. Einstein himself once wrote to the widow of a friend that for those who understand relativity, the distinction between past, present and future is only a stubbornly persistent illusion. His remark was not meant to diminish grief, but to highlight the strange geometry of space-time. If special relativity tells us that simultaneity is relative, that two observers moving differently may disagree on whether two events happened at the same time, then there can be no universal present binding all observers together. Each person carries their own slice of now, shaped by their path through space-time. The comfortable notion of a single cosmic moment shared by all evaporates. This realization gives rise to the block universe interpretation, which we encountered earlier in philosophy and now see emerging from physics. In this view, the universe is a four-dimensional block where all events, past, present and future, coexist. Your childhood birthday, the first steps of humanity on the moon, and the final sunrise billions of years hence are all equally real, simply located at different coordinates in space-time. Your sense of moving through time is not the cosmos changing, but your consciousness, tracing a path along your world line. The present feels special because that is where you happen to be aware, not because the universe itself distinguishes it. To many, this conclusion is unsettling. It seems to deny freedom, to erase becoming, to suggest that the future is already written. If the block is complete, then what we call choices are just coordinates in space-time, fixed as surely as the positions of mountains. The growing block theory we met earlier offers some comfort. The past and present are real, but the future is not yet. Still, relativity seems to resist this compromise, insisting that what counts as present is relative to motion, not absolute. And so we are left with a puzzle. Everyday experience deepens the puzzle rather than resolves it. You cannot help but feel that the present is different from the past and future. When you open a letter, when you strike a key on a piano, the sense of immediacy is overwhelming. Neuroscience tells us that even this immediacy is constructed. The brain does not process signals instantly. Light enters the eye, sound vibrates the ear, and only after tens or hundreds of milliseconds do they coalesce into awareness. What you call now is already slightly delayed, stitched together from recent inputs. In this sense, the present is a moving construction, not a direct access to reality. Memory also complicates the matter. The past seems gone, yet it leaves traces. Photographs, fossils, written records, neural patterns in the brain. These traces give the past a weight that the future lacks. The future leaves no records, and so it feels unreal. But if relativity is correct, both past and future are equally part of space-time. The difference lies not in the cosmos, but in the asymmetry of information. We have access to the past because entropy allows records to form, while the future remains hidden because it has not yet left marks. The arrow of time is a matter of entropy, not of ontology. Philosophy has long wrestled with this. Presentists cling to the intuition that only the now is real. Eternalists accept the block and try to make peace with its determinism. Some propose that the present is emergent, a feature of consciousness, not physics. Perhaps now is like the colour blue, not a fundamental feature of the universe, but a product of perception, arising from the interaction between reality and the human mind. Everyday analogies help to bring this down to earth. Imagine reading a novel. At any given moment, your awareness is fixed on the current page. The pages behind are the past. The pages ahead the future. Yet all pages exist simultaneously in the book. The story is already complete, even if you have not read it all. Or picture a film reel. Every frame exists on the strip, but you experience them one by one, creating the illusion of motion and unfolding. The present is your projector, shining awareness on a single frame at a time. What then becomes of meaning, of agency, of life itself in such a view? Some find comfort in eternalism, imagining that nothing is ever truly lost, that every moment exists forever in the block. Others find it suffocating, fearing that it robs life of spontaneity. And yet, even if the future exists, your experience of it is still one of unfolding. You do not know what will come, and in that uncertainty lies freedom. Physics may describe the block, but psychology insists on the drama of living it line by line. Julian Barber, the physicist who argued that time may not exist at all, takes the argument even further. In his view, the universe is not a block unfolding, but a collection of nows, each a complete configuration of the cosmos. Motion, change, and flow are illusions created by the way our minds link these nows together. If he is right, then not only the present but time itself is a construct. We live in a timeless collection of snapshots, stitched together by memory and perception. It is a radical idea, but it resonates with the sense that the present is slippery, never quite as solid as it feels. Perhaps the present is best understood as a collaboration. Physics provides space-time, a fabric where all events exist. Entropy provides the arrow, distinguishing past from future. Consciousness provides the spotlight, illuminating a single slice and calling it now. Together, these create the illusion of a flowing present. It is not a trick in the sense of deception, but a perspective shaped by the limits of our awareness. When you pause to breathe, to listen, to notice the moment you inhabit, you are both honouring the illusion and transcending it. The present is real enough for living, even if it is not fundamental in physics. You do not need a universal now to enjoy the sound of rain on the roof or the warmth of tea in your hands. The illusion is sufficient, perhaps even beautiful. For if the present were not special to us, we might never notice life as it happens. As we continue, we will turn from illusions of the present to wilder possibilities. If space-time is flexible, could it loop upon itself? Could there be pathways, wormholes, or cosmic twists that allow us to revisit the past or leap into the future? The block universe may dissolve the uniqueness of now, but curved space-times invite us to wonder whether time itself might bend back upon itself, allowing journeys that defy common sense. The next step in our exploration will be into these speculative territories, where physics plays with the possibility of time travel. For as long as people have told stories, they have dreamed of escaping the ordinary flow of time. Legends speak of enchanted caves where years pass in a night, of magical rivers that let travellers leap forward into the future, of gods and heroes who step outside the mortal clock. In modern times, the dream has shifted into science fiction. Time machines, paradoxes, adventures across centuries. But behind the imagination lies a serious question. Can physics allow it? Could the fabric of space-time, as described by Einstein's equations, contain paths that bend not only through space but also back into time? Einstein's general relativity describes gravity as geometry, and in geometry, loops are possible. Lines can curve, surfaces can bend, and paths can reconnect with themselves. In space-time, these loops are called closed time-like curves. If such curves exist, they would allow a traveller to move forward in time along their own world line, just as you always do, but eventually return to an earlier point, intersecting their own past. To the traveller, the journey would feel like ordinary motion, yet from the outside, it would look like a return to the past. One of the first hints came from solutions to Einstein's equations involving rotating universes. In 1949, the mathematician Kurt Gödel discovered such a solution, a universe filled with rotating matter in which time loops were possible. In Gödel's cosmos, you could in principle trace a path that brought you back to your own past. The discovery was unsettling, for it showed that relativity's equations did not forbid time travel. Instead, they seemed to allow it under certain conditions. Einstein himself was troubled by Gödel's result, for it threatened the very idea of causality. If one could travel to the past, could one change it? Later solutions added to the intrigue. Wormholes, theoretical tunnels through space-time connecting distant regions, have long been speculated about. If such a wormhole could be stabilised, and if one end were accelerated or placed near a massive object to experience time differently, then the two mouths might fall out of sync. Step through one mouth, and you could emerge not only far away in space but also earlier in time. Rotating black holes, known as Kerr black holes, also contain regions where closed time-like curves might exist, though these regions are hidden behind horizons and tangled in singularities. Each scenario raises the spectre of paradox. The most famous is the grandfather paradox. If you travel back and prevent your own ancestor from existing, how could you be born to make the journey in the first place? The paradox illustrates the tension between time travel and causality, the logical chain of cause and effect. Some physicists have suggested that consistency might protect reality. Any trip into the past would be constrained to ensure events remain self-consistent. You might travel back, but everything you do was already part of history. You could not kill your grandfather because in fact you did not. Instead, you might become the cause of events you thought you were changing. Another possibility is the many worlds interpretation, where travelling into the past would not alter your own history, but branch into a parallel timeline. In this view, you could kill your grandfather, but it would only affect that new branch, not the one you came from. You would not erase yourself, but simply end up in a different universe. This resolves the paradox, but introduces a new layer of speculation, multiplying worlds with each time-travelling act. Yet practical obstacles loom large. Wormholes, if they exist, would require exotic matter with negative energy density to remain open, something never observed in sufficient quantities. Kerr black holes are real, but their time loop regions are likely unstable, shredded by tidal forces and radiation. Even Gödel's rotating universe does not describe our cosmos, which expands rather than spins. Each mathematical pathway seems closed off by physical impossibility, as though nature allows the geometry in theory but bars it in practice. Still, the fact that relativity admits these solutions at all is remarkable. It shows that time, once thought rigid, is pliable enough to fold back upon itself in the equations. Whether the universe truly permits such folds remains an open question. The laws of thermodynamics, quantum effects, or some yet unknown principle may forbid them, preserving causality. Or perhaps, at the deepest level, reality is less concerned with causality than we are, and time travel in some form remains possible. Even without closed loops, relativity already gives us a kind of time travel. We saw earlier that moving at high speeds or living near a massive object slows time relative to others. Astronauts orbiting Earth already experience a tiny bit of this. They age slightly less than people on the ground. travel near light speed, and the effect magnifies. A ship journeying for a few years at relativistic speeds could return to find decades or centuries past on Earth. This is not science fiction, but experimental fact. Time dilation is a form of one-way travel into the future. The everyday imagination of time travel tends to focus on the past, but the future is already open. The real question is whether the past can be revisited. If the present is an illusion, and the universe is a block, perhaps every moment exists and could, in principle, be accessed. If time is emergent, perhaps it resists reversal because emergence itself has a direction. If entropy is the true arrow, then maybe past-directed travel is blocked because entropy cannot be undone. Each of these ideas points us back to the puzzle. What is time really, and why does it seem to flow only forward? Stories of time travel endure because they embody our longing. Who has not wished to undo a mistake, to relive a moment, to glimpse what lies ahead? Physics gives us glimpses of possibility, tempered by paradox. We may never build a machine with dials and levers to whisk us back to the past, but in thinking through the conditions, we discover more about the fabric of reality. The impossibility may be as instructive as the possibility. As we continue, we will leave paradoxes behind and enter the realm of quantum mechanics. There, time sometimes disappears entirely from the equations, and the quest to unite relativity with quantum theory raises the question of whether time is fundamental at all. Time travel may or may not be real, but the deeper mystery is whether time itself exists in the way we think it does. By the early 20th century, physics was being pulled in two directions. On one side stood Einstein's relativity, reshaping our understanding of space and time on cosmic scales, revealing that geometry itself bends and that time flows differently depending on motion and gravity. On the other side stood quantum mechanics, born from the puzzling behaviour of atoms and light, which replaced certainty with probability and made the smallest scales of reality dance to strange and unpredictable rules. For a while, these two revolutions ran on parallel tracks. Relativity described the very large, quantum mechanics the very small. But eventually, they had to meet. The first great attempt at reconciliation came from a British physicist named Paul Dirac. Dirac was a quiet and meticulous man, known for speaking sparingly but thinking deeply. In the late 1920s, he set out to build an equation that would unite the principles of quantum mechanics with the demands of special relativity. Quantum theory alone could describe the electron, but it did not account for relativity's requirement that no particle can exceed the speed of light. Relativity alone could describe motion near light speed, but said nothing of the strange probabilities and wave-like nature of particles. Dirac sought an equation that respected both. The result was astonishing. His equation not only fit the known properties of the electron, but also predicted something entirely new: the existence of antimatter. According to the mathematics, for every particle there should exist a mirror partner with the same mass but opposite charge. For the electron, this partner was the positron. At first, this seemed like an abstract artifact of the math, but in 1932, Carl Anderson discovered the positron in cosmic rays, proving Dirac right. It was the first particle of antimatter ever observed. This discovery showed that the marriage of relativity and quantum theory could generate profound new insights. It also deepened our understanding of time. The Dirac equation allowed solutions that could be interpreted as particles travelling backward in time. This interpretation, though controversial, suggested a symmetry. What we call antiparticles might be particles moving in reverse temporal direction. Richard Feynman later popularised this view in his diagrams, where antiparticles appear as ordinary particles traced backward in time. Whether literally true or simply a mathematical trick, the connection revealed how intertwined time is with the fabric of quantum fields. Antimatter itself is strange and beautiful. When a particle and its antiparticle meet, they annihilate, releasing energy in a burst of photons. The process is perfectly symmetric, yet the universe we inhabit is made overwhelmingly of matter. Where did all the antimatter go? This imbalance is one of the deepest mysteries of cosmology. If the laws of physics treat matter and antimatter equally, then the Big Bang should have produced them in equal amounts, annihilating everything into light. But somehow, a tiny excess of matter survived, enough to form stars, planets, and you. The reason for this asymmetry may lie in subtle violations of time symmetry at the quantum level, a hint that time itself may not be as reversible as equations suggest. In everyday life, you rarely encounter antimatter because it vanishes instantly when it meets matter, yet it is not purely theoretical. Hospitals use positrons in PET scans, where particles annihilate inside the body to produce images. Particle accelerators routinely create and study antiparticles. In these laboratories, the interplay of relativity and quantum mechanics is not abstract, but practical. Time dilation, energy mass equivalence, and quantum probabilities all work together to describe what is observed. Dirac's work also highlighted a deeper issue known as the problem of time. In his framework, time was still an external parameter, a backdrop against which particles evolved. Quantum mechanics in general relies on such a parameter. The Schrödinger equation tells us how a wave function changes with time, assuming time already exists as a given. Relativity, by contrast, treats time as part of the dynamical fabric. It can stretch, bend, and even disappear inside horizons. Reconciling these views remains a central challenge. Dirac managed to build a bridge, but the full unification of relativity and quantum theory, the elusive theory of everything, still escapes us. The philosophical implications of antimatter are rich. If antiparticles can be seen as particles travelling backward in time, then time is not a one-way street in the equations. The laws themselves are symmetric. A film of two electrons scattering can be run forward or backward, and the mathematics make sense either way. The asymmetry we experience, the fact that eggs break but do not unbreak, that we remember yesterday but not tomorrow, must come from something beyond the fundamental equations. It comes from entropy, from initial conditions, from the way the universe began. In the deep grammar of physics, time is reversible. In the poetry of life, it is not. Imagine for a moment watching waves break on a shore. You know instinctively that the scene could never run in reverse, that the foam will not gather itself back into a perfect crest. Yet at the level of atoms and particles, nothing forbids it. Each molecule of water could, in principle, trace back its path. Antimatter, with its suggestion of backward time travel, reminds us of this tension. The arrow we experience emerges not from the equations, but from the improbability of reversal. Dirac's quiet genius left us with more than equations. He left us with a reminder that the universe may be stranger than imagination, that new realities can emerge from the demand that two principles coexist. He gave us antimatter, a shadow twin to the matter we know, and in doing so he opened a window into the symmetry of time itself. As we move forward, we will step more deeply into this problem of time. The Wheeler-DeWitt equation, born from attempts to quantize gravity, will show us a universe where time drops out entirely, where the cosmos seems frozen, timeless, awaiting interpretation. Rovelli and others will argue that time is relational, emerging from correlations rather than flowing as an independent river. The timelessness of quantum gravity is a profound challenge, one that forces us to ask whether time exists at all, or whether it is an emergent story we tell to make sense of change. By the mid-20th century, physicists had built two astonishingly successful theories. General relativity described the large, planets, stars, galaxies, and the structure of space-time itself. Quantum mechanics describe the small, atoms, particles, forces, and probabilities. Each worked beautifully within its own domain, but when physicists tried to combine them, cracks appeared. At the heart of those cracks lay an uncomfortable truth. The two theories disagreed on the role of time. Relativity treated time as elastic, curved, inseparable from space. Quantum mechanics treated time as fixed, external, and absolute. Reconciling these views led to one of the strangest equations in physics, the Wheeler-DeWitt equation, which seems to erase time altogether. John Wheeler and Bryce DeWitt developed their equation in the 1960s, trying to quantize general relativity, to apply the rules of quantum mechanics to the geometry of space-time. The result was startling. An equation that described the quantum state of the entire universe, but in which no time variable appeared. Unlike the Schrödinger equation, which tells us how a wave function evolves with time, the Wheeler-DeWitt equation simply states relationships between different configurations of the universe. The cosmos in this picture is not something that unfolds through moments, but something frozen, timeless, and all at once reality. At first, this seems impossible to reconcile with experience. We clearly feel time passing. We remember the past, anticipate the future, and live in a continuous flow. How can physics tell us that time is absent? Wheeler himself admitted the discomfort. He called the disappearance of time a crisis for physics, not because the equation was wrong, but because it conflicted with human intuition. If the ultimate theory of the universe contains no time, then our experience of its passage must be emergent, an illusion born from deeper processes. Carlo Rovelli, one of the architects of loop quantum gravity, has embraced this view. He argues that time is not fundamental but relational. In his picture, the universe consists not of objects moving through a background, but of networks of relationships. Time emerges from the way things change relative to each other. Imagine two clocks. Alone, neither defines time, but when compared, one ticking faster, one slower, the relation creates a sense of before and after. Extend this to the universe as a whole, and time is not a river flowing independently, but a story we tell about correlations. To make this less abstract, think of a symphony. Each instrument plays notes, not in isolation but in relation to the others. The rhythm emerges from these interactions. Time, Rovelli suggests, is like that rhythm. It is not a separate thing, but a pattern in the way events connect. Without events, without relations, there is no time. In this sense, Aristotle's old idea, that time is the measure of change, finds a new home in quantum gravity. Experiments with quantum clocks hint at this relational view. Physicists have begun to place atomic clocks in superpositions, making them exist in states of ticking at different rates simultaneously. These experiments suggest that at the quantum level, even time can be entangled, blurred, made relative in ways we do not yet fully grasp. When two particles are entangled, their states are correlated no matter the distance. Perhaps time itself is an entanglement, a web of correlations from which our perception of flow arises. The timeless universe has unsettling implications. If time is not fundamental, then the universe has no beginning and no end in the ordinary sense. The Big Bang is not the first moment, but one configuration among many in the cosmic wave function. The heat death is not a final moment, but another configuration. Past, present, and future lose their distinctions. All that exists is the structure of possibilities, with our consciousness tracing a path through them. But perhaps this is not as alien as it sounds. Consider again your own experience of the present. Neuroscience tells us that what you feel as now is already stitched together from delays, from processes that take tens or hundreds of milliseconds. You do not perceive time directly. You perceive correlations between events, the sound of a word, the movement of lips, the echo of memory. In that sense, even human perception treats time relationally. The Wheeler-DeWitt equation may simply extend this truth to the entire cosmos. There is also a gentle poetry in imagining a timeless universe. Instead of a river flowing from source to sea, think of a landscape, complete and eternal. Every hill and valley, every path and stone exists at once. Walking through it gives the illusion of sequence, but the land itself does not change. Our lives, in this vision, are journeys across the terrain of possibility, each step revealing a new vista, though all vistas are already there. Yet we must be cautious. The absence of time in the Wheeler-DeWitt equation may signal not the literal absence of time, but the incompleteness of our theories. It may mean that we have not yet discovered the right way to merge relativity and quantum mechanics. Other approaches, such as string theory, preserve time as a fundamental element. Physics has not settled the question, but the very fact that time can vanish from the equations at all shows us that our intuitions are not sacred. The universe is not obliged to conform to human feeling. Whether time is fundamental or emergent, the problem forces us to see more clearly what we mean by time in the first place. Is it the ticking of a clock, the expansion of the universe, the increase of entropy, or the rhythm of correlations? Perhaps it is all of these, at different scales and perspectives. Like light, which is both particle and wave depending on how we measure it, time may have multiple natures. At the most fundamental level, it may dissolve into relationships and structures, but at the human scale it returns as flow, as history, as story. As we move forward, we will look at one of the most intriguing possibilities to emerge from this relational view, that space-time itself may arise from quantum entanglement. If time is not fundamental, perhaps space is not either. Perhaps both are woven from information, from the invisible threads of correlation that bind the universe. In this way, the timeless universe may not be a void, but a hidden loom, weaving the fabric of reality from threads that lie deeper than space or time. In the long search to reconcile quantum mechanics and general relativity, a curious idea has gained strength. Perhaps space and time are not the foundation of reality at all. Perhaps they are built from something deeper, something woven from the invisible fabric of correlations. Just as temperature is not a fundamental property but arises from the collective motion of countless particles, so too might space-time itself emerge from the interplay of quantum information. In this vision, the universe does not begin with space and time. It begins with relations, and what we call space-time is the tapestry those relations weave. The key to this idea lies in quantum entanglement. When two particles are entangled, their properties are linked no matter how far apart they travel. Measure the spin of one, and the spin of the other is instantly determined, even across light years of separation. This phenomenon baffled Einstein, who called it spooky action at a distance, yet it has been confirmed countless times in experiments. Entanglement shows us that the universe is not a collection of isolated parts, but a web of correlations, a system where connections matter as much as objects. In recent decades, theoretical physicists have found that entanglement may do more than create strange correlations. It may actually stitch space-time together. This idea arises most clearly in the study of black holes and the so-called holographic principle. According to this principle, proposed by Gerard T. Hooft and Leonard Susskind, and developed further in the ADS/CFT correspondence by Juan Maldacena, everything inside a volume of space can be described by information encoded on its boundary, like a hologram. In this framework, space-time inside the volume is not fundamental but emergent, arising from the entanglement structure of the boundary theory. Think of a tapestry. From a distance, it looks like an image, a deer in a forest, a river winding through hills. Up close, you see threads crossing, knotting, binding. The picture emerges from those connections, not from any single thread. In the same way, space-time may be the large-scale image, while entanglement is the threads. Without the threads, the picture vanishes. Without entanglement, space-time itself dissolves. This perspective helps illuminate puzzles about black holes. According to classical relativity, information that falls into a black hole is lost forever. According to quantum mechanics, information cannot be destroyed. The conflict is known as the black hole information paradox. In holographic models, the paradox resolves. The information is not lost but encoded in correlations on the boundary. Space-time inside the black hole, including its horizon and singularity, is emergent, a geometry created by entanglement. The apparent destruction of information is an artifact of treating space-time as fundamental when it is not. Everyday analogies can bring the idea closer. Consider a computer screen. You see shapes, letters, colours, moving images. But beneath those appearances lie bits of information, ones and zeros, linked in patterns. The world on the screen is emergent, not fundamental. In the same way, our sense of being in space, of moving through time, may be the emergent screen of reality, with quantum information playing the hidden role of code. Or think of a friendship. The bond between two people is not a physical object, yet it is real, and from it arise shared experiences, shared places, and shared meaning. Relationships create structure. Perhaps the universe itself is such a network of relationships, and what we call space-time is the structure that arises from their weave. The phrase it from qubit has become a shorthand for this idea. A qubit, the quantum bit, is the smallest unit of quantum information. If space-time arises from entanglement, then reality is not built from particles or fields alone, but from qubits. The geometry of the universe is the geometry of information. Space is what it feels like to be entangled. Time is what it feels like to trace those correlations. Matter, energy, and gravity are not primitive but emergent. This vision transforms our sense of time. If time emerges from correlations, then its flow is not an independent river, but the unfolding of entanglement. The arrow of time may be the arrow of information spreading, networks becoming more entangled, correlations becoming more complex. This connects naturally with entropy, which is itself a measure of information. The second law of thermodynamics, which drives time forward, may be a reflection of the universe's entanglement structure. As correlations deepen, entropy rises, and the flow of time is born. Some physicists imagine that the entire universe is like a vast quantum computer, processing information, generating correlations, and in the process giving rise to the geometry we call space-time. In this picture, the Big Bang was not the creation of space and time from nothing but the ignition of entanglement, the beginning of the network from which space and time unfolded. The present moment is simply the current state of that computation, and the future is the continuation of its algorithm. Yet here, too, we must be cautious. The mathematics of ADS/CFT and holography applies most cleanly to universes with certain symmetries, not to ours exactly. The leap from elegant models to ultimate reality remains speculative. Still, the hints are compelling. Each time physicists test entanglement, they find it more fundamental than expected. Each time they examine space-time, they find it more fragile, more emergent, more dependent on underlying structures. The convergence is difficult to ignore. For philosophy, the implications are profound. If space and time are emergent, then they may not exist independently of the universe's deeper reality. They may be conveniences, stories told at a certain scale, like temperature or pressure, useful but not fundamental. We might live in a cosmos where the true fabric is not space-time but information, not positions and durations but patterns and correlations. To ask where and when may be like asking how hot in a world that has not yet formed matter. The question makes sense only once the emergent property exists. For us, living inside the emergent screen, the illusion is complete. We feel ourselves in rooms, cities, planets, galaxies. We watch clocks tick and stars age. The geometry feels solid, undeniable. Yet beneath it all may lie only networks of entanglement, whispering to each other across scales we cannot perceive. The solidity of space and the flow of time may be like the solidity of a rainbow, real enough to see, but dependent on deeper conditions, vanishing if those conditions change. As we prepare to close this part of the journey, we stand at a threshold. The timeless universe of the Wheeler-DeWitt equation told us that time may not be fundamental. Entanglement and emergent space-time suggest that space, too, may not be. What remains is information, correlations, relations. In the next sessions, we will explore the final hypotheses: string theory, loop quantum gravity, and other attempts to describe the deepest level of reality. Each offers a different picture, but all converge on the same unsettling possibility: space and time, the stage upon which all our stories unfold, may themselves be illusions. For decades, physicists have searched for a single framework that unites the two great pillars of modern science, general relativity and quantum mechanics. Relativity tells us that space-time bends and curves, creating the architecture of the cosmos. Quantum mechanics tells us that matter and energy flicker in uncertainty, governed by probabilities and entanglement. Yet when we try to apply both at once to describe what happens inside black holes or at the very beginning of the universe, the theories clash. Out of this tension arose two of the most ambitious projects in theoretical physics, string theory and loop quantum gravity. Both claim to reveal the fundamental structure beneath space and time, and though they differ profoundly in method and vision, both whisper the same unsettling idea, that space and time may not be what they seem. String theory begins with a radical simplicity. Instead of treating particles as point-like dots, it imagines them as tiny vibrating strings. The different vibrational patterns of a string give rise to the different particles we observe: electrons, quarks, photons, gluons. Just as a violin string can play many notes depending on how it vibrates, so too can fundamental strings produce the diverse spectrum of matter and forces. The mathematics of string theory is elegant, but it comes with surprising requirements. For the equations to be consistent, strings must vibrate in more than the familiar 3 dimensions of space and 1 of time. Depending on the version, the universe may require 10, 11, or even 26 dimensions. Most of these extra dimensions are thought to be curled up so tightly that we cannot perceive them, like threads woven too fine to be seen by the naked eye. In string theory, gravity is not a mysterious external force, but the natural vibration of a string, one of its fundamental modes. This unites gravity with the other forces of nature, something that no other theory has done successfully. Moreover, string theory naturally incorporates quantum mechanics, allowing space-time itself to be described in a quantum way. Yet the theory is vast and complex, filled with countless possible solutions. Physicists speak of a landscape of possible universes, each with different values of constants, different shapes of compactified dimensions, different laws of physics. Ours is one of them, but why this one exists rather than another remains uncertain. Loop quantum gravity takes a different path. Instead of replacing particles with strings, it focuses directly on space-time. General relativity treats space-time as smooth, a continuous fabric. Loop quantum gravity suggests that this smoothness is an illusion, valid only at large scales. At the smallest scales, space-time is quantized, made of discrete units. Imagine a woven cloth. From afar it looks smooth. Up close you see the threads and knots. According to loop quantum gravity, space-time is like that cloth, built from loops of quantum fields linked in networks. These loops form a spin network, a mathematical web that gives rise to space. Time, in this view, emerges from changes in the network. The implications are striking. In loop quantum gravity, there is no infinite divisibility of space. Areas and volumes come in smallest possible units, indivisible quanta. This eliminates the singularities that plague general relativity, such as the infinite density at the centre of a black hole or at the Big Bang. Instead, black holes have finite cores and the Big Bang becomes a big bounce, a transition from a previous contracting universe to our expanding one. The timeless Wheeler-DeWitt equation finds a natural home here, with time emerging not as an external parameter, but as a property of how spin networks evolve. Both string theory and loop quantum gravity aim to answer the same question: what is space-time made of? String theory suggests it is woven from vibrations of fundamental strings in higher dimensions. Loop quantum gravity suggests it is woven from discrete loops of information, the quantum threads of geometry itself. Neither theory has yet been experimentally confirmed. String theory is criticised for its vast landscape of solutions and lack of testable predictions. Loop quantum gravity is praised for its conceptual clarity, but struggles to connect with particle physics. Each has its strengths and weaknesses, yet both embody the same boldness: to look beyond space-time and imagine a deeper structure. For everyday intuition, both theories can be grounded in analogies. String theory is like music. Each note is a vibration, and the universe is a symphony of strings. The violin, the cello, the flute, all instruments are made from the same underlying principle: vibrating air. In the same way, all particles and forces may be vibrations of the same string. Loop quantum gravity is like pixels in a digital image. Up close, you see individual dots. From afar, you see a continuous picture. Space may be digital in this sense, the smallest unit of area and volume, invisible at our scale, but real in the foundation. Philosophically, both theories echo earlier debates. Newton imagined absolute space and time as real entities. Leibniz argued that only relations matter. String theory, with its hidden dimensions and continuous fabric, feels closer to Newton's vision of an ultimate stage. Loop quantum gravity, with its emphasis on networks of relations, feels close to Leibniz. Perhaps both were right in part, perhaps neither. The very fact that their argument still resonates centuries later shows how deeply the question runs. As you sit here listening, you may wonder, why does this matter for your life? After all, whether the universe is made of strings or loops, the clock still ticks, the tea still cools, the night sky still gleams with stars. Yet beneath those ordinary rhythms lies a profound truth. The very framework that allows clocks, tea and stars to exist may not be what it seems. If space and time are emergent, then the present moment, the place you inhabit, is a product of deeper laws we have only begun to glimpse. To know this is to see the world differently, to sense the mystery in each second, to realise that reality may be as strange as any dream. As we prepare for the final stage of our journey, we will step back from technical theories and ask the ultimate question. If space and time are not fundamental, what are they? Illusions, emergent phenomena, conveniences of perception? Or are they something more subtle, questions the universe asks through us? In the next session, we will bring together the threads: relativity, quantum mechanics, entropy, and emergence, and reflect on what they tell us about the nature of reality itself. We have wandered far, from ancient philosophers under starlit skies to black holes at the end of the universe, from Newton's ticking clockwork to quantum loops and vibrating strings. Along the way, time has slipped through our fingers like water. We tried to grasp it as an absolute, and it dissolved into relativity. We tried to capture it in equations, and it disappeared from the Wheeler-DeWitt framework. We treated it as fundamental, and physicists like Carlo Rovelli told us it is relational, a story of correlations. Julian Barber went further still, insisting that only nows exist, that time itself is an illusion stitched together by memory. Each step has left us with more mystery than before, and yet that mystery is not despairing. It is rich, calming, almost musical. Think of how our understanding has shifted. Once time was the heartbeat of the cosmos, ticking the same everywhere, a river flowing evenly from past to future. Relativity bent it, showed that it ticks differently for each observer, that gravity slows it down and speed dilates it. Thermodynamics gave it direction, the arrow of entropy pulling us forward, leaving records of the past but not of the future. Quantum mechanics blurred it, made it uncertain, entangled, even emergent. And at the deepest level, theories suggest it may not exist at all. What seemed most obvious, the passage of time, is perhaps the most elusive. The same is true of space. Once we thought of it as a stage, an infinite backdrop where events unfold. But Minkowski fused it with time, Einstein bent it, and holography now hints that it is stitched from entanglement. Loop quantum gravity imagines it pixelated, woven from discrete loops. String theory suggests it is woven from hidden dimensions, invisible but real. In all these views, space is not ultimate. It is a fabric, a tapestry, a screen on which information plays. Just as time dissolves into correlations, space dissolves into relationships. What, then, are we to make of our lives, lived in rooms and fields, measured in hours and days? Are they illusions? The answer depends on what we mean by illusion. A rainbow is not a solid arch, yet it is real enough to see. A mirage is not an oasis, yet it is a genuine pattern of light in the air. Illusions are not nothing. They are phenomena arising from deeper structures. If time and space are illusions, they are not empty tricks, but the most profound illusions imaginable, ones that allow galaxies, consciousness and love to exist. They are the stage and the music, emergent yet indispensable. Lee Smolin insists that time is real, that to deny its reality is to lose what matters most, the openness of the future, the possibility of novelty, the chance for the universe to create. Julian Barber insists the opposite, that only nows exist, timeless and complete, and that our sense of passage is a projection. Between these poles lies a truth we may never fully capture. Perhaps time is real for us, emergent but binding, like the melody of a song that exists only when played. Perhaps space is the harmony, arising from entanglement but giving shape to all we know. Even entropy, the arrow that seemed so merciless, becomes gentle when we step back. Without entropy's rise, stars would not shine, rivers would not flow and life would not exist. The heat-death, that quiet horizon in the far future, is not cruelty but completion, the balancing of all gradients. To live in a universe with entropy is to live in a universe that changes, and changes the condition for everything we hold dear. Time's arrow, drawn by entropy, is the same arrow that points you toward tomorrow morning, toward laughter, toward memory. So we arrive at stillness, not as an ending but as a perspective. Beyond all theories, beyond relativity, beyond entanglement, there is the simple experience of now. You sit in a room, you feel your breath, you hear the soft hum of the world around you. The clock ticks, but you need not chase it. Whether the universe is timeless or flowing, whether the block exists or the future is open, what is given to you is this moment. Perhaps that is what time really is. Not an entity or a dimension, but the gift of attention, the thread that lets us live. The speculative civilization we imagined at the beginning, clinging to a black hole to stretch their hours, sought to escape the inevitable. Yet even for them, the real treasure was not the length of their days, but the moments they lived within them. You too do not need a time machine or a cosmic equation to find meaning in time. You need only to notice it, to savour the warmth of tea, the rhythm of footsteps, the glance of a loved one, the silence between words. In these simple things, the mystery of time is alive. Perhaps the final truth is that space and time are questions, not answers. They are mysteries the universe asks through us. When you wonder about time, you are time reflecting on itself. When you measure space, you are space aware of its own reach. We are not outside time, looking in. We are threads in its weave, part of its fabric, inseparable from its question. And so, Our journey closes not with certainty, but with quiet wonder. Space and time may be illusions, emergent phenomena, shadows of something deeper, or they may be real in ways we cannot yet define. Either way, they are enough. They give us a universe of stars, a world of change, and a life filled with moments. That is more than enough. So rest now. Let the questions drift like constellations across the night. Let the mystery of time cradle you. Sleep well, little thread in the loom of the cosmos. You're not outside space and time, you're its story, folded gently into the answer.